Okay, so we are set up. So let me just do a quick intro and then we can get started. So we're very happy to have Sivateja giving us a guest lecture today on Stein's method. So Sivateja is a faculty member at Georgia Tech, and he has done many sort of notable research projects over the years. I just mentioned one of them, which is a personal favorite of mine. So this was on the crossbar switch. This is a notoriously hard queuing network control problem. And I know personally, I was like, this has got to be solved as a PhD student, right? When it was a wide open question, I said one has to solve this question. It can't possibly be open for that long. And I spent 6 months and I made no progress. So the centerpiece of Sivateja's thesis was that he actually solved this problem during his PhD. And then he's made it a business to be able to analyze finite complicated queuing systems without sort of taking asymptotic limits and get very tight results. Recently, he's also applied it to finite sample guarantees for reinforcement learning, among many other topics. So we are very excited to learn from you today, Sivateja. So over to you.
Thanks, Yash, for that very generous introduction. So I'm not going to talk about the crossbar switch work that Yash mentioned today, but in the very last part, I'll talk about a much simpler system, a single server queue, in which I present some of the ideas that played a central role in studying the crossbar switch. Okay, so thanks, Yash, again for giving me this opportunity to speak. I've been thinking about Stein's method for a very long time. I used it in some of my research, but I think I'm only still scratching the surface of its power. So this is a good opportunity for me to kind of go through everything, crystallize my thoughts, and so on. I tried to make notes on this, and then I shared it through a Dropbox link. I guess all of you have it. I updated the file like half an hour ago. So if you downloaded the file earlier, please go back and download it again. So before I start, let me make it clear that most of what I'm going to talk about, like the first 3 parts in particular, are actually not my work. This is work that happened in various communities over the last few decades, 3 to 4 decades. I'm kind of trying to summarize them here. And then in the very last part on the single server queue, that is actually my work. So the outline for today's talk, this is the first time I'm actually going to, I'm giving a talk that is 3 hours long. So hopefully I'll survive by the end of this. So since this is 3 hours long, I want to give an outline and make sure I stick with the time. So I'll first start with a brief introduction of Stein's method. That will be a short part. And then I'll go ahead and start talking about Stein's method for normal approximation. These 2 parts together will constitute about an hour of our discussion today. And then we'll take a short 10-minute break. And then I will, so at the end of the second part, I'm going to state a big theorem on Stein's method for normal approximation. That's a very abstract theorem. I'm going to show how it can be used by establishing rate of convergence of central limit theorem. I'll do that in the third part. This will also last about 1 hour. After that, I'll take a 10-minute break again. And then finally, we'll move on to the last part where I'll talk about single server queue and then show that Stein's method can be applied here as well. But this time, instead of normal approximation, we'll have exponential approximation. And with that, I think we come to the end. I guess this will be the end of the talk, end of the semester, and also end of this year. Feel free to interrupt me at any point of time. In fact, I really like if it is interactive. And moreover, I don't really know what you guys have seen in this course so far and so on. So if anything is not clear, feel free to ask questions. It's okay even if I don't get to do everything. The most important thing for you guys is to understand the stuff as opposed to me trying to do everything. Okay, cool. So let's get started with part 1. So what is Stein's method? What is the objective in Stein's method? The problem that Stein's method is trying to solve is to bound the distance between 2 distributions. So in this talk, I'm going to keep the terminology fairly vague. So I'll use measures and distributions interchangeably. I can't do this in a paper, but for ease of understanding and exposition, for me, distribution and measure is the same thing. So there are two distributions or measures, and then I want to bound the distance between them. And so firstly, to talk about this, I need to explain to you what distance between measures is. There are many notions of distances. We'll talk about a few and we'll focus on one particular distance, the Stein distance. So why is this interesting? So many times in probability theory and applied probability, we have a sequence of random variables. And then we want to say that the sequence converges to a limit. Then you may have seen that there are many different notions of convergence in probability theory. Almost sure convergence mean square, convergence in probability, convergence in distribution, and so on. And each of them have different definitions. But in this process, we usually don't talk about distance. When you talk about convergence of real numbers, it's all defined in terms of distance. But some notions of convergence of probability don't use distance. Now, once you have certain convergence result of this form, then the next question is, what is rate of convergence? So to talk about rate of convergence, I essentially need to bound the distance between the nth guy in the series, in the sequence, and the limiting object. And if I show that this bound is like 1 over n or 1 over n square or whatever, then these quantities essentially establish my rate of convergence. So bounding, if I know how to bound distance between two distributions, then I can use it to establish rates of convergence. And this is the main reason that Stein's method is used. But when I'm talking about bounding this distance, I actually don't have to think about the whole sequence. I just look at the one object in the sequence, the nth guy, and then bound the distance. So these are the kind of applications that I'm going to show today. Okay, distance, as you all know, should satisfy three properties. Any bivariate function that satisfies the three properties is a distance. And one of the three properties is that it is symmetric. Distance of x from x to z should be equal to distance of z to x. So this suggests that whatever method I develop whatever analysis I do can be symmetric in x and z, that I can interchange x and z. A counterintuitive thing about Stein's method is that it actually doesn't treat these two objects at the same level. In fact, it thinks of the z as a special object. So much so that I can't actually talk about Stein's method in general to bound distance between two distributions. I can, but we will not talk about it, at least for most of today. Instead, there is a separate Stein's method for each z. So suppose I want to show, I'm interested in central limit theorem. Let's say I normalize everything so that the limiting object is standard normal. Then to show distance of some distribution with respect to the standard normal, I develop one method. If I want to show distance to the Poisson, I have to start from scratch and develop another Stein's method. If I have to show distance to the exponential, then I have to develop another Stein's method also. So this actually sounds very roundabout and complicated, but turns out that each of these methods can be developed by following a template. And I'll actually illustrate one of those for normal approximation. And then once the method is developed, that is like a one-shot thing. For example, for normal approximation, the method was developed in 70s or 80s, I believe. And then since then, it has been applied in many problems. So today we'll focus on the case when z is normal, in particular standard normal, Gaussian with mean 0 and variance 1. And then we'll also focus on the case when it is exponential distribution. So we'll look at two limit theorems, where the first one is central limit theorem, where we converge to normal. The second one is a queuing application, where you converge to exponential, and we'll establish rates of convergence. Of course, if you are not interested in a standard distribution like normal, exponential, Poisson, if you make up your favorite distribution and you want to find the distance to it, there is now prescription to develop Stein's method for your favorite distribution. I'll not get into too much details of it, but at some point I'll mention that as well. Okay, so before I get started on Stein's method per se, the first thing we need to understand is distance between two distributions. So let's say I have two random variables that come from two distributions, x and y. I said I'll use distributions and measures interchangeably. Sometimes I also don't make distinction between the random variable and its distribution also during the course of this talk. Okay, I want to, so there are many distances one can define. I'll look at a particular class of distances that look like this. So to define my distance, the first thing I need is to fix a class of functions. I can pick my favorite class of functions. And then for each of this function, I calculate expectation of this function for my random variable x and for random variable y, and look at the difference between them, and look at the worst case over my entire class. That's defined to be the distance between these two random variables. One can verify that this is indeed a distance. I'll not do so here. So let's see examples of distances that fall into this framework. The first one is Kolmogorov distance or Kolmogorov metric. Here, what functions am I using? So this is usually denoted, at least today, using dk. And the function class I use is the class of step functions. So pick your favorite real number x, and then look at a function that looks like this. Up to x, it is 0. From x, it is 1. And by changing x, I have a whole family of functions. And if I look at these functions and then take their expectation, then I get Kolmogorov distance. Essentially, these functions are saying, that I basically look at probability x less than or equal to x minus probability y less than or equal to x. So essentially, I'm looking at the CDF. CDF is a function. Look at the difference between the CDF at every value, and then look at the worst possible thing that gives you the Kolmogorov distance. So in particular, if you remember central limit theorem, I'll recap it later. Central limit theorem talks about convergence in distribution, which means convergence of CDFs, the cumulative distribution functions. So, which means this is central limit theorem is essentially talking about convergence in this metric, in the Kolmogorov metric. Okay, the second metric that also fits into this framework and which we will primarily focus on is the Wasserstein distance. And here I work with the class of functions that are, one Lipschitz. So these are all R2R functions that satisfy this inequality for all x comma y, which means they're Lipschitz functions with Lipschitz parameter 1. So, and then I'll denote this by dw x comma y for Wasserstein distance. And this is the same as before. Maybe I can copy paste. I think I could have written it faster than this. Okay, anyway, so why is Wasserstein distance useful? It has many nice properties. Yesh itself, Yesh knows much more about Wasserstein distance than I do. It has interpretation in terms of transporting probability mass and so on. But it turns out that it also is related to the Kolmogorov distance. So there is the following well-known relation. I will not really use it, so I'll not prove it. So if I show that Wasserstein distance between two distributions is bounded, then I can also bound the Kolmogorov distance between them. And in particular, if I have a sequence of random variables x, x1, x2, and so on, and then I show that the distance to y decays in according to some rate, then I immediately have a rate of convergence on the Kolmogorov distance as well, even though I get a square root here. So at least I have, if I have convergence in Wasserstein, that implies convergence in Kolmogorov or weak convergence or convergence in distribution. That's one nice thing about Wasserstein distance. And the second thing is, so Wasserstein distance is the worst case error between these quantities, where I'm looking at the entire class of one Lipschitz functions. A particular case of one Lipschitz function is the usual linear function, h of x equal to x. So if I use this function here, essentially I'm looking at the mean of x and mean of y, and then I'm looking at the distance between them. So if I show convergence in Wasserstein, then that means that I also have convergence in mean. So these are two nice properties of Wasserstein distance. Okay, then the third metric that falls into this framework is the total variation distance. Here, the H class is basically indicator functions of Borel sets. For Kolmogorov distance, we used indicator functions of intervals, intervals from -infinity to x in particular. Here we'll use here one uses indicator function of Borel sets. We'll not really be using it. Any questions so far? So I'm now, this ends part 1 introduction. Now I'm going to move to part 2 on Stein's method for normal approximation. Okay, you guys have been too quiet for my taste. So let me ask you a question. So suppose I'm interested in standard normal. I want you to tell me what a standard normal is. How would you describe a standard normal?
The question is, what is the standard normal?
Standard normal distribution, mean zero variance, one Gaussian. This is not a trick question. This is, I mean, undergrad probability question. How would you describe any distribution?
Density or CDF or PDF.
Good. So you can describe any distribution by giving it CDF. If it's continuous, then you can talk about its density. So for example, for standard normal, we know its density is the usual thing, 2 pi, I guess. A CDF, there's no closed form expression, but there is a formula, I mean, there's a notation. And then you also know that an MGF or a characteristic function also completely describes a distribution. So in MGF, I'm essentially looking at something like this. This is a Laplace transform of the PDF and characteristic function. It's essentially the same thing. Instead of theta being a real number, I think of it as a imaginary number, j omega. Okay, so then, and in fact, for standard normal, the MGF is like this, e power theta square over 2, and the characteristic function is like this, e power minus omega square over 2. I remove theta, put j omega, I'll get minus omega square. Okay, so what we are going to use in Stein's method is actually none of these descriptions. Stein's method essentially says that there is yet another way of thinking about distributions in terms of operators. So instead of thinking of distribution as a standalone object, think of it in terms of what it does to other guys. So whenever I have a distribution or a random variable, I can take a function and then take expectation. So this whole thing can be thought of as an operator. So I have my random variable x, you give me a function h, using my x, I'll give you a number which essentially happens to be this. This can be thought of as an operator. So before going into the operator viewpoint, let me first start with a lemma. So let's say Z is a standard normal. In all of this part, in part 2, or most of this part, I'm going to use Z to denote standard normal. And I'll use W to denote another distribution. So basically my goal is to bound this where Z is standard normal. And then I'll develop Stein's method to do this. In particular, there are 2 primary ingredients in Stein's method, Stein operator and Stein's equation. And the Stein operator is basically a way of describing the distribution, yet another way of describing the distribution in addition to all these viewpoints. Okay, good. So let's say Z is my standard normal, and let's say F is an arbitrary function. Okay, when I say arbitrary, I don't want you to go too crazy and think of Cantor functions and things like that. So I want it to be nice enough. What is nice enough? Absolutely continuous. The derivative, if it is absolutely continuous, almost everywhere a derivative exists. And then I assume that this derivative satisfies the following bound. Whatever the derivative is, take its expectation with respect to standard normal, it should be fine. So if you don't understand what these terms mean, don't worry about it. Just think of it as a nice enough function. And this is a very, very, very broad class of functions. Okay. The point of this lemma is that if my Z is standard normal, it satisfies the following equation. I'll call this equation 1. Okay. Oh, by the way, the numbering of lemmas and theorems is weird because I kept moving around my notes, but I'll use the same numbering as my notes so that it's easier for you to look it up in case you're trying to look up as I talk. Okay, good. So what is this? I don't know. I mean, I just wrote some weird equation. The magical thing about this is true for pretty much any function f. That is the key. That is the key issue here. As long as z is standard normal, I don't care what function you give me. For any function f, this equation holds true. Let's actually prove this. So to prove this, I'll start with the right-hand side. So, and then I can write this using just my definition of expectation. So I know my PDF of standard normal, f is this given distribution, and then minus infinity to infinity. So now how do I do this integral? So somehow I should get a f here. There is a f dash. So if I do integration by parts, things should look good. So that is one way of doing it. I can simply do integration by parts. And then when I do that, somehow I should differentiate this and then nx will show up. I'll get something like this. Instead, instead I'll do it slightly differently, which makes it slightly easier to present. So I'll first split this into two parts, the negative part and the positive part. And then let's look at the first part. Okay, this is the weird thing. So here I have this function e power minus x square over 2. What do I get if I differentiate it? If I differentiate it, I'll get e power minus x square over 2. If I differentiate, I'll get x e power minus x square over 2 with a minus, I think. Okay, so here I'll put this function minus x e power minus x square over 2, but instead of x, I'm using t. And then I'll integrate this from minus infinity to x. I can do this using fundamental theorem of calculus. I have some nice function here. I don't like it. So I'm differentiating it and then putting an integral. That's all. And then I'll do the same thing for the other term, which will be basically the same thing with the limits changed. Here it should be x to infinity. That's it. Okay. Now I'll interchange the order of the two integrals. Whenever I have two integrals, that's the first thing everybody is tempted to do. And then I'll not worry too much if it is allowed or not, because I can always invoke Fubini's theorem. Minus infinity to x, minus infinity to 0, f dash of x dx, plus essentially the same thing here. Then this is simply f of t. Sorry. When I change the order of integrals, I should basically change the limits carefully. So you should just draw a picture and figure out what the limits are going to be. I'm going to write it from my notes. Okay, cool. And then for the second thing, you'll get something similar. And now I have integral of the integral of this guy, and from t to 0, but there is a negative. So at the end of the day, I'll get a f of t, and I'll get a similar thing here. So if I combine both these terms, I'm going to get minus infinity to infinity, t e power minus t square over 2, f of t dt. Okay, so there's nothing much here. This is just basic calculus. So I'm skipping steps. Again, there are two ways of doing it. One is take this blindly, do integration by parts. The second one is I artificially change this to its integral of its derivative, and then change the order of limits and play around with the terms. Then this gives me f of t, and I get this at the end of the day. Okay, then this is nothing but expectation of z f of z. This is my Gaussian PDF. So the function I have now is tf of t. So this is the expectation of z f of z. And that's essentially what I claimed. Okay, why do I care about this? Because the converse is true. This is what makes the whole thing very, very interesting. And this is called Stein's lemma. So what this says is that suppose I have a random variable z. I don't know what it is. I don't know its distribution, but I happen to know that no matter what function you give me, my z satisfies this equation. Then z must be standard normal. So to state this, I'll write this in terms of an operator. So instead of writing, so I'll define an operator that looks like this. What's an operator? It takes a function and spits out a function. So if you give me a function f of x, I apply this operator, you'll get a new function, function of x, and the new function of x is this guy. So essentially what I have here, this equation is same as saying expectation of this operator applied to z is 0. So if you look at both of this together, you'll see that this is just another way of writing. This operator is basically just this thing. Okay. Okay. So what Stein's lemma says is that if z is a standard normal, firstly, for all nice enough functions, same condition as I wrote before, expectation of a f of z equal to 0. We already proved this, so I don't have to prove this again. The second part is the converse. What it says is I have some other distribution, some random variable w. I don't know its distribution, but suppose I happen to know that this is 0 for, again, same for all absolutely continuous functions with this condition, then z must be a standard normal. Z is same as w in distribution. Okay, so essentially what this is saying is that I can think of this operator as yet another way of describing a standard normal. So we know about PDF, CDF, and so on. Another way of describing a function, by the way, is in terms of the moments. Describing a distribution is in terms of the moments. If I give you all the moments of a distribution, then I essentially know the distribution. This is not quite correct because in some cases you can't find it uniquely. But for as long as you have sub-exponential tails, then all the moments completely characterize the distribution. What is a moment? Moment is basically expectation of x power m for all m, which means I'm calculating expectation of h of x, where h is the monomial x power m. And then I'm doing this for all monomials. This is the same as saying I'm doing this for all polynomials. So essentially, one way of describing a distribution is to tell what happens when you take all possible polynomials and take its expectation. Another way is to talk about all possible exponentials and taking the expectation, that is the MGF. Here, what it is saying is that take your favorite function, but instead of applying expectation to that function, introduce this operator, then you should get 0. And this operator now essentially characterizes my distribution. And in the case of normal, the operator looks like this. Now, for any distribution, for Poisson, I can come up with a different operator which satisfies essentially the same lemma. For exponential, I can come up with yet another operator. So at the end of the day, whenever I want to bound a distance of this form, the first thing I should do is, for my favorite distribution z, I should come up with an operator to bound these distances. Okay. So how do we prove this? So I already proved part 1 of the lemma. I have to prove part 2 of the lemma. So to prove part 2 of the lemma, let me first state yet another lemma. This almost sounds like I'm pulling something out of the hat, but once you have this lemma, This lemma is going to be easy to prove. Once you have this lemma, proving Stein's lemma is going to be very easy. So consider, let's say, consider the following differential equation. So the differential equation is trying to solve for a function. Normally you think of a function as f of x. Here I'm writing it as f of w because x means something else for me. So think of x as a fixed real number. If x is a fixed real number, this is a constant. What is this? This is the CDF of standard normal. Find the CDF of standard normal at that value x. And then this is my step function. And now my objective is for a given x, I want to find a function f of w that satisfies this. As you can see, this is on the left-hand side, I basically have the operator that I defined here. It's the same operator. So essentially, I want to prove the Stein's lemma. And then for this, I pulled up a differential equation. I just made it up. I pulled it out of a hat. And then I'm saying, consider this differential equation. And then the claim of this lemma is that the unique bounded solution of this differential equation is something that looks like this. Okay, fine, whatever, some complicated thing. Why is this interesting? We'll use it in a minute to prove the previous lemma. Let's quickly do the proof of this. The proof is actually just 3 lines. First, consider the following function, e power minus omega m or w square over 2 times f, and then look at its derivative. This is just product rule of differentiation. And now I can pull this e power minus w square over 2 outside. What I'll have left over is this f dash minus w f of w. That is essentially what I have in the ODE. So this should be equal to this. Therefore, I can substitute the right hand side. Now that's it. So I have derivative of something equal to this thing. X is a fixed quantity. W is my variable here. So which means the solution of this is simply integral of the right hand side. I have to integrate it carefully. So if I do it, I'll get something like this. I'll also possibly get some constant. And then it can be shown that this constant must be 0. If this constant is not 0, this function will not be bounded. For any non-zero constant, this will not be bounded. Therefore, we should take c equal to 0. Then I get this. Okay, fine. This is just a lemma, but our main objective is to prove this. Let's now prove this. So what do I want to prove? The second part of lemma 3, which is that if for any distribution, this is true for all functions f, then the distribution must be Gaussian. Okay, now I'm going to use the lemma 2. What I'll do is this equation here is true for any function f. Only thing is it should be absolutely continuous, derivative should exist, and derivative should have finite mean. So I can pick my favorite functions and put here, substitute here. And of course, my favorite function is this thing. That's why I worked hard to construct this. So basically, I have 0 equal to expectation of this operator applied to this function. And this function comes from here. And notice that whatever the solution is, I don't care about the solution actually. I did the math here to show that this differential equation has a solution. And the solution, since I have an explicit form, if you are worried if the derivative of this exists, you take derivative and then you just check. If you're worried if the expectation of the derivative is finite or not, since you have a closed form expression for this, you can just substitute and check. Okay, now that I know that this differential equation has a solution, I can just use the differential equation. The differential equation is essentially saying that the operator A applied to my f gives me this. So I can substitute for this over here. So this is expectation of indicator. Again, notice that here fix x. X is some fixed real number, arbitrary real number. And all my expectations are with respect to W. Okay. Now, if I look at this guy, expectation of indicator is probability. And this is just a number. X is a fixed number. So expectation doesn't do anything. So essentially, what do I have? I have that. What is this? W. So this is basically the CDF of W. Sorry, just a second. Okay, so I'm given that my W satisfies this equation, and it's true for all F's. I substitute F that I got by solving this particular ODE. I don't care about what the solution is anyway, but the ODE that it satisfies is this guy is equal to this. So this should be a capital W, sorry. Okay, then, yeah, then what do I have? I have CDF of W. This is CDF of W is equal to CDF of standard normal. That means W is the standard normal. Any questions?
Siva, can I ask one question?
Sure.
So what's the intuition of this functional operator form? If it's normal, it's some function derivative minus x times that function. But if it's some other distribution other than normal, how do you come up with?
I will talk about it. So the one-line answer is that this operator is simply the generator of a Markov process whose stationary distribution is the distribution that you're interested in. So one Markov process whose stationary distribution is Gaussian is the OU process, Ornstein-Uhlenbeck process. So this operator is simply the generator of OU process. So if I want to find the Stein operator for exponential, find your favorite Markov process whose stationary distribution is exponential, and then that'll give you a Stein operator. I'll talk more about this once I'm done with the main results. That's a great question. So that essentially lets us know how to come up with these operators more generally. Okay, good. So what did we achieve so far? In fact, I actually showed you all the proofs so far. I didn't skip anything. The only thing I skipped is mathematical details. Using very simple math, we showed that this operator characterizes the standard normal. So we know that if there is some distribution where for every function, this guy is 0, then that distribution should be standard normal. Now, suppose I have a distribution W where this is not 0. But if it is small, can I say that my W should be close to standard normal in some sense? Because when this is 0 for all functions, I know W must be standard normal. Can I now interpolate this idea and say that if this guy is small for all functions, then W should somehow be close to Z. Then what function should I care about? So this idea can be made formal in the following theorem, which is essentially the main result, Stein's method for normal approximation. So let's say W is some random variable and Z is standard normal. Now consider the class of functions that looks like this. It's the set of all possible functions whose so the norm for functions throughout this talk is going to be the L infinity norm. So I'm looking at class of functions which are differentiable at least 2 times. And then the L infinity norm of this class of functions should be 2. The L infinity norm of the derivative is some number square root of 2 over pi. L infinity norm of their second derivative should be bounded by 2. Okay, whatever, where is this coming from? I have no clue at this point. We'll see when we do the proof. But the point is that if you look at these functions and apply my operator A to all the functions in this class, so now I'm restricting my function class. I'm not saying your favorite function. I'm saying this is still a fairly large class, but not arbitrary function. So as long as you find a function from this class and then apply this A operator to these functions and take expectation, and then look at the worst possible value in this. And this essentially gives me the Wasserstein distance between W and C. So in particular, this theorem already subsumes the lemma. So if I have a W where for all these functions, this guy is 0, that means the Wasserstein distance should be 0, which means W and Z should have the same distribution. So this already subsumes the lemma, but this goes further and says that when this is not 0, if this is some number, that number is a bound on the Wasserstein distance. So to be explicit, another way of writing this is expectation f dash of W minus W f of W. Okay. So Wasserstein distance, remember, we defined it in terms of like this. It is basically distance between the expectations when these test functions are coming from one Lipschitz class. Okay. Now in the theorem, I don't have any one Lipschitz anywhere here. I don't have any one Lipschitz, but I have this weird function class f. Where does this come from? It should somehow be related to the one Lipschitz class. Indeed, that is true. We'll see how it is related. And this is where the Stein's equation comes into picture. So I'm now going to prove this. Any questions about the theorem? So what we're going to do next is I'm going to spend the next 20 minutes or so proving this theorem. After I prove this theorem, I'll explain how it can be used in practice. So in particular, I'll use it to establish rate of convergence of central limit theorem. And then I'll also talk at a high level. I'll make some comments about where these operators are coming from, all of that stuff. This is a good point to ask any questions, because I'm going into the proof now. Okay, so I'll first present the proof idea more generally, not just for Wasserstein. The idea can be used anywhere, but we'll actually do the proof for Wasserstein. So let's say that I want to bound the general distance between these two guys. And at the end of the day, I want the right-hand side to look something like this, except that this class will, of course, depend on this class somehow. So this we know is defined to be like this: h of W minus h of Z. And I want to show, but I don't want this here. Instead, I want something like this. So what I do is, based on this, I again, from my hat, pull up a ODE. Sorry, what is my ODE? H of X minus H of, you know what, I'll use X. I don't want to change notation relative to my notes because I'll goof up. Okay, H of X minus expectation of H of Z is equal to A f H of X. Suppose I happen to find a function. So I want to find this distance and then maximize it over all possible H. Let's fix a H for a moment. For a fixed H, suppose I find a new function f H that satisfies this relation. This has some derivatives in it and all that. So this is some kind of ODE. So suppose that is true. So let me actually write this equation more explicitly. What is this equation? I'm just simply writing the A operator explicitly on the right hand side. And then I don't know why I'm flipping it from right to left. So this is the equation 2 in my notes. And this is equation 4. Sorry about that. These are not in the right order. So, okay, suppose I happen to find a FH that satisfies this equation. At this point, I don't know if such a FH exists. I randomly wrote some equation. There may not be a solution. There are all those issues. Then this guy will be equal to sup of H of A f H of W. Sorry, X. This is what I wanted on the right hand side. Now, the only issue is that for every function H, I should go solve this differential equation, find FH, and then take sup over all those H's. So this equation is called the Stein equation. And then the way we brought it up is almost wishful thinking. I really wish, I hope my Christmas present this year is that the solution for this equation exists for every H. If that exists, then I'm very happy. And then I hope I also know that solution. Then I can take sup over that class of solutions of this H. You give me your favorite H from the original class, one Lipschitz, for example. Then I find FH that solves the Stein equation for those H's. And among all those FHs, sorry, there's an expectation here. I'll calculate the sup of this and that should give me my Wasserstein distance. So which means I have to solve this Stein equation. This is an important ingredient in Stein's method. To prove this theorem, the main part is solving the Stein equation. But actually, you know what? You don't have to solve the Stein equation. So all I'm doing is for every h, I have to find the corresponding fh, right? Instead of that, suppose I find that all these fhs satisfy some property. All these fhs for any h, this fh belongs to some class, let's say. Suppose I prove something like this. I don't know how to solve for fh, but I show that it has some property. Then I can further upper bound this guy by this class. Okay, and then I'll get a theorem that looks kind of like what we have for the Stein's theorem. Now, how do we go and bound this in any application of interest? That's completely orthogonal, and that's what we'll talk in the next part. So let's actually make this work in practice. So now I'm going to present the proof of this theorem. Essentially, this is what I'm going to do. I'll basically solve the Stein equation, and then instead of using the exact solution, I'll collect some properties of all the solutions. I'll define the class of functions that have those properties. In fact, that class turns out to be this. So essentially, where did I get this? If your h is the one Lipschitz function, then I'll solve the Stein equation for any one Lipschitz function, and that solution lives in this class. That's where this class comes from. Okay, let's actually do all of this. So let me first solve the Stein equation for the standard normal. So let's consider the Stein equation again. Now again, I'm using w as the dummy variable instead of x. I think I should probably streamline notation. Okay, so the Stein equation is simply this. Okay, by the way, if this h happened to be the step function, the indicator function w less than or equal to x, then this Stein equation is same as the equation that we had, that we had here. I'm saying this is a times f is equal to, think of this as h of x. Then this is the expectation of h under the standard normal, which is just a CDF. So essentially, this is the Stein equation. That's why I pulled it out of a hat. But here I generalized it further. Instead of indicator functions of intervals, I'm looking at more general h, which can be one Lipschitz, for example. Okay, so the solution of this is given by e power minus w square over 2 infinity to w. Where do I have it? Infinity to w, minus infinity to w, sorry, minus e power minus t square over 2 expectation of h of z. Remember, z is standard normal, expectation of h of z is some number for the purpose of this solving the differential equation. Okay, whatever. So like before, I have this equation that came out of the hat, the Stein's equation, and then you solve it. I'm not going to do the proof of this lemma. It's not hard, but it's just more math, that's all. And then the solution happens to be like this, some complicated thing. I don't really care about this. What I care more is the following. Suppose h is bounded, then whatever the solution is, it satisfies the following inequalities. It so whatever this complicated function is, I mean, this is a beast. I can't manipulate this. But then using this, you can notice that if I take the infinity norm of this whole function, it is bounded by something like this. The infinity norm of h shows up here. So this thing here is a function. And I'm looking at infinity norm of this. And similarly, if I take its derivative and look at the infinity norm, it satisfies something else. Actually, I think I don't need the first part. I could have skipped it. The second part of this is what I need. If h is absolutely continuous, then then it satisfies the following three relations. It's first, the infinity norm of f itself satisfies this bound. The infinity norm of its derivative again satisfies a bound. Infinity norm of its double derivative satisfies this. In particular, if h is 1 Lipschitz, then h dash, the infinity norm of h dash should be, so sorry, this is the end of the lemma, end of the statement of the lemma. I'm not going to prove this, but essentially in this lemma, I solve the Stein's equation. That is an important ingredient of the method. Okay, now at the end of the day, I'm going to be interested in Wasserstein distance, and Wasserstein distance says that h, the test function, should be 1 Lipschitz. So if h is 1 Lipschitz, then the infinity norm of h dash is bounded by 1. Then the f will be bounded by just number 2. I can basically drop this h dashes here. If I drop this h dashes here, then essentially I get the function class. Sorry, where is this? This function class. Okay, so if I drop the h dash here, if I put 1, then f is bounded by 2, f dash bounded by this number, f double dash is bounded by 2. That's essentially my function class. So I'm almost there. Let me now do the proof of the theorem. Okay, so I want to find the Wasserstein distance between W and Z, Z in standard normal. By definition of Wasserstein distance, this is same as this difference between the means where the sup is taken over 1 Lipschitz functions. And then for all, you give me any h, the way I wrote down my Stein equation is that you give me any h, and then I want to solve this equation. H of x minus h of z is this. This is a function equation. X is a variable. Here, think of this as a number, and think of this w as a variable. And then essentially, this is same as a h of w. Sorry, a f h of w. Okay, so why? fh solves this equation. If I remove x, put a capital W, I'll essentially get this. I have to put an expectation also. So think of this as a fixed number, and think of basically this expectation. This expectation is basically this expectation. Okay, good. And then now I know exact formula for fh for every h, but I don't want to use it. It's so messy. But I know that whatever this fh guy is, it satisfies all these things. And then I know that my h dash is 1. So therefore, I can simply write this as sup f belongs to f. And where f is basically any function that satisfies these inequalities with ones here. That's exactly how I define my function class f. So that's it. This completes the proof. Any questions? So again, one important thing to notice about this theorem, the main theorem. Maybe I should put a box or something. I could have used a different color. This is the main theorem in this part. One important thing to notice is that I want to Z is standard normal. W is the distribution I'm interested in. I want to find the distance between these two. The right-hand side has no standard normal in it. I have to bound some quantity, certain expectations of some functions which come from some class and all that. But this expectation only involves W. There is no Z. Where did Z go? Z went into this operator. Z characterizes this operator basically. So that is one nice thing about Stein's method. If I want to show a sequence of random variables is converging to some limiting object, then the bounds that I need to do don't involve the limiting object. I have to somehow bound these terms, and in that process, I don't have to care about the limiting object. So let me summarize. I'll take a short break, but before that, let me summarize. So Stein's method can be thought of as in 3 steps. So if I want to do Stein's method for my favorite distribution, now suppose Z is, so summary of this part. So suppose Z is my favorite distribution, need not be standard normal. Now I want to find a way of bounding this. Then step 1 is find the operator, find Stein operator for Z. So if you want to do it for Poisson, you should find a Stein operator for Z. This was the question that I got earlier. And what do I mean by that? This is 0 if and only if this Y guy has same distribution as Z. And where do we get these operators? Like I said, those come from generators of Markov process. If you don't know what it is, if time permits, I'll explain that in more detail. The second step is pull a Stein equation out of a hat that looks like this. Z is now your favorite distribution, need not be standard normal. So you write down this Stein equation and then worry if it can be solved or not. This is by far the hardest part in some sense. Solving this equation, writing the equation is very easy. I already did that. Solving it is the hard part. So many a time you may not be able to solve it. If you can't solve it, it's enough if you show that a solution exists and you can collect some properties of the solution, even though you don't know the explicit formula. You put all those properties in a function class F, in a set F, call that cursive F. So let F be a function class consisting of solutions of Stein equation. Then step 3 is basically replicate these 3 steps. You don't even have to change these 3 steps. And then once you do that, you'll get that in any distance. Need not be Z here, need not be standard normal, H need not be Wasserstein. For any distance, you can get, for appropriate function class, you'll get a result like this. The function class, of course, depends on the solution of the Stein equation and also on this H, the class from which this H is, the little h that this function is coming from. Okay, so I think if you really want to understand this, I mean, this is all very, in terms of ingredients, there is nothing fancy. This is all just expectations, functions, simple differential equations. There's nothing, there's no heavyweight machinery, but the way of thinking here is somehow counterintuitive. It's backward thinking in a way. So I think one gets used to this the more one stares at this. One way of doing it is to kind of go through this exercise but for a different distribution and a different metric, let's say for exponential distribution, and then replicate a theorem that looks like this for Stein's method for exponential approximation, Stein's method for Poisson approximation. Then I think you would understand all these steps very clearly. Unfortunately, I'm not going to have time to do that, but most of what I'm doing here is based on a survey paper by Nathan Ross, and he does this again and again for many different distributions. Okay, I think this is a good time for a break. So let's meet in 10 minutes. I'm going to hang around, so feel free to ask any questions in the meantime.
I have a question. Yeah, so in the step 1 that you mentioned, so like in order to prove this, like the indicator like F that you had, that's enough, right? Irrespective of what Z is.
What you're saying is to prove step 1, this is where we proved step 1. You're saying to prove step 1, you have to solve this kind of thing. Is that what you're asking?
Yeah, for irrespective of the operator.
Irrespective of no, the operator shows up here, right?
Oh, yeah.
Okay, so what you're saying is that to prove step 1, you have to actually solve Stein equation for indicator functions. Is that what you're saying?
Yeah.
That is correct. In fact, actually, if you really want to prove something like theorem 3, you don't have to do step 1. You don't have to do lemma 3. So if you look at my proof of theorem 6, proof of theorem 6 is only 3 lines. The only thing I used in the 3 lines is here I used lemma 5. When I went from this H to F, I'm using the fact that the solution satisfies this. I did not use lemma 2, I did not use lemma 3. So lemma 2 and lemma 3, I presented here mostly for exposition reasons. Actually, the reason I did not use lemma 3 is because lemma 3 is subsumed here. Here I solved a more general Stein equation. In lemma 3, I only solved a special case of it. So in reality, you don't have to actually prove that the operator characterizes your distribution, but the operator you come up with, it better really characterize, even though you don't have to prove it in the proof step, because when you prove the theorem, when you do something like lemma 5, you're proving something even more powerful and more general. Yeah. In other words, if you solve Stein equation in full generality for any H, you don't have to solve it specifically for indicator. Does that answer your question? Okay. I don't know if I can make you guys bigger. Okay. Okay, I think this is much better.
I have a question.
Yes, Anirudh. Thanks for stopping by the way.
I have a short question. So in this step, when you're saying H is absolutely continuous, lemma 5 point number 2, you're saying FH has a certain property. So you know those properties are true for FH because you have an explicit solution for FH written in the second line.
Correct. Correct.
So you really need the explicit solution to know that.
No, what I'm saying is for this Stein equation, finding the solution is not hard. So I was able to find it. Now, suppose you're interested in some other distribution and you want to solve the Stein equation for that. And maybe your distribution is so complicated that you don't know how to solve the Stein equation.
Right.
Then, I mean, this is basically at the end of the day solving a differential equation, right? The best thing about a differential equation is if you solve it and show the unique solution is unique, life is good. Suppose you can't do that, then what you can do is show that a solution exists and then show that it satisfies some properties like this. Maybe that is easier than finding the solution, right? If you have the solution, then you can spin off how many other properties that you like.
So my question is, so there are situations where people have been able to do this, where they can't solve the Stein
Yeah, they have, yes, a lot.
without having to solve the Stein.
If you go beyond normal, if you want to do it for your favorite distribution, for example, one set of distributions that people have looked at is the following. So I said normal is the stationary distribution of OU process, right? Then OU process is a particular form of a stochastic differential equation, but you can come up with your favorite stochastic differential equation. If it's nice enough, it'll have some stationary distribution. What is it? I have no clue, but I want to find distance with respect to that stationary distribution. These kind of questions arise in queuing theory. And they are not able to solve the Stein equation for these weird distributions, but they're able to prove some properties which they exploit.
So those properties are provable even when you don't know what is the stationary distribution.
Correct. Correct. You don't know the stationary distribution, you don't know the solution of Stein equation, but you know some properties. People have actually developed machinery to get this kind of property. So it's not like a one-off thing. So this is like a very well-established area. People have spent everything that I'm saying, every step becomes very complicated if you go to other cases. And each and every step, people have developed like extensive methods. But I mean, it's always possible to come up with yet another problem where the steps are hard.
I mean, because it's very easy to write down a stochastic differential equation whose stationary distribution I don't know.
Exactly.
It's very trivial to write a simple SD whose stationary distribution I won't know.
No, I'm not saying they did this for all SDs. So
but you're
they look at some queuing problem. They're interested in particular specific SDs. For those SDs, at least after struggling for a lot of time, they are able to get these properties, even though they don't know the solution of the Stein equation or the stationary distribution.
So the outcome of this process.
It'd be good to see some examples like that.
I can give you pointers. Anton Braverman's work does this basically. Anton Braverman and Jim Rai. Yes.
So just to understand, so the outcome of all this will be that you prove that the distribution of the Markov chain converges to that steady state distribution, even though you don't explicitly characterize the steady state distribution in those cases.
In which case? Oh, in those cases, in the Braverman stuff.
Yeah.
Okay, no. There it is slightly different. What they want to do is the following. So in the later part, I'm going to talk about heavy traffic, right? So they have some system and then they want to understand its some queuing system. They want to understand its stationary distribution. That is the problem. Okay, think of GG1Q. You want to understand stationary distribution of GG1Q. There is no closed form expression. There are numerical methods and so on, but you cannot find the distribution explicitly. Now, what you want to say is that, okay, I can't find the distribution explicitly, so I look at some asymptotic regime, maybe heavy traffic regime. In the heavy traffic regime, do the stationary distributions converge to something? The answer is yes, and they converge to exponential. That's what we'll see in the later part. Now, what Jim and Braverman are doing is that they look at more, not a single server queue, they look at more complicated queue. You can't find the stationary distribution. The question is, do the sequence of stationary distributions converge to something in the heavy traffic limit? And for that, what they do is they guess the answer is yes. Now, what is this limiting distribution? They guess that the limiting distribution should come from an RBM. Why do they think this? Because of the whole diffusion limit machinery.
It should come from what?
The limiting distribution is the stationary distribution of an RBM, of a reflected Brownian motion process, or some stochastic differential equation more broadly. And why do they think this should be the answer? Because this is actually proved that at a process level, the sequence of queuing systems in the heavy traffic limit, the entire stochastic process will converge under appropriate scaling to the corresponding SDE. But what they are trying to achieve is that they want to show rate of convergence for the steady state distribution. So basically, based on all these prior results, they have reasons to believe that the limiting distribution is stationary distribution of an SDE. So now if you develop Stein's method for that particular stationary distribution, then you can establish rate of convergence of your sequence of stationary distributions. And that is what they do.
I have a question.
And sorry, one more comment. What they do is very, very fascinating, but in some sense, it is limited to certain settings. You mentioned about switch scheduling. You can't do all of this for switch scheduling because of the multi-dimensional state space collapse issue. And the main challenge in preventing this is again the step of solving the Stein's equation. Or in other words, finding, if I can't solve it, I just have to find some properties, right? Finding these properties is again the hard part. Question?
Oh yeah, so you mentioned that the operator comes from the generator of the OU process. But typically I've seen that the generator actually, like for an OU process, actually involves like a double prime. And then there's another.
Yeah. So I think what I did is,
on the first
so look at the generator of OU process. I think it is like F double. Let's apply it to G instead of F. It is like G double dash minus something, and then define G dash to be F. Then you get this. That's all.
I see. But it seems like if it comes from a generator whose markup of the markup process whose stationary distribution matches the distribution that you want, then couldn't there theoretically be many different generators that you could possibly...
Exactly. That's a good point. So I said that Stein operator for your favorite distribution is just generator of a markup process whose stationary distribution is your favorite distribution, right? Oh my God, that's a mouthful. So there are many markup processes that can have the same stationary distribution. So I can come up with many operators, and that is true. You can come up with your favorite operator, but at least in the literature for popular distributions, there are specific operators that people have looked at. For Gaussian, this is the operator, because whenever you think of Gaussian, usually the first thing people think of is OU process. You can of course make up some other markup process, get another Stein operator, but then the Stein equation will be different. Then again, you have to solve it and so on. Sometimes using a different operator might be useful. I haven't, for exponential, I know that there are at least 2 or 3 different operators. I haven't seen them in the context of Stein's method, but I've seen them in other contexts.
I mean, for instance, one would imagine just looking at this, let's say for the first time, right, that depending on what metric you care about, like a different generator might be the right one to get the tightest bounds.
Correct. That is quite possible. Yes. Yes. Maybe that's why people use this thing for Wasserstein distance. For Wasserstein distance, maybe this operator is the best thing. I don't know for sure. Maybe that's why people ended up on this.
But it seems like now.
But actually, now that we're talking about this, do you guys know of any other markup process whose stationary distribution is Gaussian?
So you can do all kinds of stuff. Like you can just be like, I'm going to flip the sign after some time, after some random time, and that will still be.
Well, yeah. In fact, I mean, that is what we exploit in CLT in some sense. I'll not present it the way you explained, but the proof I'm going to present can be rewritten in the way you said.
Oh.
Yeah. Sorry, I think someone was trying to make another comment.
I was also wondering, because at least for a Gaussian, like, you know that the generator is really nice because you also know that it's like, the eigenfunctions are like Hermite polynomials. So I was wondering, can you use the polynomials in order to, like, let's suppose you wanted to bound like not just the Wasserstein distance, but like for higher order moments.
Okay.
You use somehow like the fact that there are these eigenfunctions for the.
I see. Okay, maybe I don't know. I don't know for sure, but I can totally understand. So you're saying instead of Wasserstein distance, maybe you go to Wasserstein 2, Wasserstein 3, or whatever different distance. Then maybe these properties alone are not enough. Maybe you have to look at other properties that you exploit this these eigenfunctions of the operator. Yeah, maybe. Like I said, the literature here is vast. I'm not really an expert in this. Like I'm kind of trying to pick up. So yeah. Okay, so welcome back. And then let's go to the second part. So to give you a recap, we finished introduction and various notions of distance. We basically came up with the Stein's method, the main theorem for normal approximation. It said that to bound distance to standard normal, you have to bound certain quantity on the right hand side. And then at this point, this is a very abstract theorem, but quite powerful. Now I want to show you how this can be used. And one place where standard normal shows up is central limit theorem. So you all know central limit theorem. So I want to find the rate of convergence in central limit theorem. So rate of convergence. So okay, good. Let's start doing it. Okay, so let's recap central limit theorem. So theorem 1 came now. Lemma 2. We started with lemma 2. Whatever. So x1, x2, and so on are IID random variables. Let's say mean is finite and we can always center them so that mean is 0, variance is 1. I'm just making these assumptions. These are without a lot of generality clearly. That will make my writing slightly easier. And then I look at the scaled centered versions. Central limit theorem essentially says that this Wn converges to standard normal in distribution, which means more specifically, the CDFs of Wn converge to the CDF of standard normal in the limit. And again, remember, this is CDF of standard normal. So any of you know how to prove central limit theorem?
Characteristic function.
Okay, cool. Yeah, there are many ways of proving central limit theorem, but the simplest, I guess, is using characteristic function. So what you do is look at this guy, take its characteristic function, and then show that in the limit, the characteristic function converges to characteristic function of standard normal. And in that process, you have to worry about the characteristic function of this. And then when you have IID random variables and you add them, the characteristic functions just get multiplied. That makes it very, very easy. Okay, so I'm not going to do this characteristic function proof. This can be found in any standard textbook on stochastic process or even my lecture notes on stochastic process. I wish I had time to do that, but I think I'll run out of time, so I'll skip that. Now, I'm interested in the rate of convergence, which means I want to bound the distance between these two, which means I have to bound the Kolmogorov distance between this guy and the standard normal. Okay, that's what is done in Berry-Esseen theorem. So Berry-Esseen theorem. This is theorem 8 in my notes. So what it says is that same, these are IID random variables, mean 0, variance 1. You make yet another extra assumption in addition to what is in central limit theorem. And then W is same as before, Z is standard normal. Then Berry-Esseen theorem says that the CDFs can be bounded something like this. Okay, so I need the third moment because that shows up in the rate of convergence. So the main punchline here is the rate of convergence is square root of n. So this is somehow interesting. There is a square root of n showing up in central limit theorem itself. This square root of n, this square root of n need not be same. I mean, a priori, there's no reason to believe this rate of convergence should be square root of n. So, but turns out that's the correct answer. And I believe that it is known, it is proved that this cannot be improved. I think there's a counterexample or whatever when this moment is not finite. I don't know, maybe this constant can be improved. Okay, Berry-Esseen proved this almost a century ago. I don't think I actually looked at the proof, or maybe I did at some point. If I did, I forgot. But their proof is not easy. It's painful proof. Maybe what they do is they take this characteristic function proof of convergence, and then if you have bounds on the distance between characteristic functions, you can somehow convert it into Kolmogorov distance bounds. And I think that is what they deploy to get this. There's a way of doing that, but I don't know if Berry-Esseen do it or someone else do it. But bottom line is the way Berry and Esseen proved it's painful. What we are going to prove is, by the way, we can prove something like this using Stein's method. We're not going to do that. So to prove this, basically, this is the Kolmogorov distance, right? Kolmogorov distance between these two guys. And so if I want to prove this version in Kolmogorov distance, then I have to go back to my theorem 3 and theorem 6, and then I have to develop theorem 6 for Kolmogorov distance. This can be done. But again, if I want to do this, then I have to solve the Stein equation for indicator functions. Lipschitz functions are nice because they're differentiable, all of that. The test functions for Kolmogorov distance, Kolmogorov metric are these indicator functions, the step functions. The step functions are slightly painful because it's a gem. So if you know how to solve the Stein's equation for those step functions, actually we did that earlier. Then you can develop a variant of this for it'll look exactly like this. There'll be a K here, and this class will be different. Then I can use that new theorem to prove the Berry-Esseen theorem. But one thing to remember is that it is quite well known that if you use Stein's method, you'll not get the right constant. You'll only get a worse constant. And people know that Stein's method does not give right constants. Okay, so that is something we could do, but we are not doing it. Instead, I will prove a Wasserstein distance bound. So same as before, IID, mean 0, variance 1, but I'm assuming that the fourth moment exists. Berry-Esseen only need a third moment, but I'm assuming fourth moment. Okay, and then actually, you know what? I'm going to state this even more generally. So let me write this properly then. So x1, x2, and so on are independent random variables, need not be identically distributed. Okay, they're independent random variables, need not be identical, but they all are normalized, mean 0, variance 1. And then they all have this fourth moment condition. And then W is same as before. And Z is standard normal. So then the bound here looks like this. because they're not identical, the summations depend on x's. But suppose, so this is the theorem. Now, suppose they are IID, then let me use a terminology. Let's say all these third moments are beta 3s and all the fourth moments are beta 4s. Then the theorem is essentially saying, well, this is general, this is hard to parse with the summations and so on. That's why I want to look at the IID case. The third moment divided by square root of n times square root of fourth moment divided by square root of n. Okay, so the bottom line is that this is still square root of n convergence. I had to make a stronger fourth moment assumption as opposed to Berry-Esseen, but actually I get stronger Wasserstein distance bound. Remember, Wasserstein convergence implies Kolmogorov convergence. So convergence in Wasserstein is a stronger result. So I made a stronger assumption and I got a stronger result. So it turns out that, okay, under the stronger assumption, I immediately have 1 over square root of n convergence for Kolmogorov as well. But I mean, the fourth moment shows up in the bound. So, so under the stronger assumption, this kind of implies this, which is a slightly different constant over here. But more generally, it can be shown that these two do not imply each other. Here you relax the fourth moment to third moment. And then because of that, you have to pay the price of going from Wasserstein to the weaker Kolmogorov. Or conversely, if you, relative to this, if you make a stronger assumption, you'll get a stronger convergence. Okay, so that's the result. Let's actually prove this now. I hate this going back and forth here. Can I do, I don't know, can I copy this and then put it somewhere close by and then make it very, very small. You can still read this, right? I take that as a yes. Yeah, I can't write this small, but at least I think you can read it. Okay, cool. So proof of not the Berry-Esseen itself, but the Wasserstein variant.
How this is a stronger result?
Sorry, is there a question? I can't hear you.
Yeah. Can you repeat how this is a stronger result?
Because if I forget about the rate of convergence for a moment, if I show convergence in Wasserstein, that implies convergence in Kolmogorov.
Oh.
In that sense, it is stronger. So Wasserstein, therefore, is a stronger notion of distance than Kolmogorov, whatever that means. Stronger only makes sense when you talk about convergence. So so that's why this is a bound on the Wasserstein. In that sense, it is stronger. That's all. But I guess if you go and put it back here, then Kolmogorov is square root of Wasserstein. So you'll get another n power 1/4. So I think it is, the rate is not that good, but the notion of convergence is, the metric is a stronger metric in some sense. Okay, so proof of theorem 7. What is my objective? I want to bound this guy, the distance, which means I have to bound this right hand side, which means I basically have to bound this. So all I have to worry about is take my Wn. Wn again is simply the square root of n scaled empirical averages. I have to show that my Wn, if I take my Wn and calculate this guy, now again notice there is no standard normal inside these terms. Now I blindly have to, now I forget about Stein's method, I forget about Stein operator, I forget about everything we did in first part. All I care about is this theorem here. I don't care how this was proved. All I need to do is bound these terms for my Wn. If I show that these terms for f from this class can be bounded in this manner, that's it. My proof is complete. So this is what Stein's method lets you do. It kind of abstracts away certain difficulties, and then at the end of the day, all you have to do is bound certain quantities. And of course, Stein's method does not know what W you are going to use this for, right? So Stein's method is not going to tell you how to bound this. You have to come up with your own techniques based on your WN, based on the structure of your WN. Whatever you know about it, you have to use all of those things to bound this. So that's what we'll see in action right now. By the way, historically, I was saying that Berry and Esseen proved their theorem almost 100 years ago. And Stein basically came up with some version of this proof in 70s or 80s, maybe 70s, maybe not 80s, in 70s. And initially, it all seemed magical. My understanding is that initially, nobody knew where that operator came from. They found that operator, and then they found that the standard normal satisfies it, and they thought this was magical, and then they proved all these results. And over time, people discovered that it is simply the generator of OU process, and then that discovery enabled them to generalize to other settings and so on and so forth. Okay, cool. So I have to bound these things. Expectation is linear, so I can bound this and this separately and then put them together. Let me start with the second term. So I have to bound expectation of W f of W. Okay, so I'll introduce a notation. So for the proof of the theorem, let's say n is fixed. So even in the statement of the theorem, you can think of n as being fixed. There is no limit anywhere. That's the main thing about rate of convergence results or finite time bounds. These are called finite time bounds because there is no limit in the theorem. So for any n, this is true. So think of n as being fixed. So whatever this Wn is, I'll simply call it as W for the purpose of the proof. Okay. But I'm going to confuse you by introducing a slightly different notation. I'll now introduce Wi. So Wn is simply W. W is basically the n is fixed. W is this guy. I define Wi as essentially the same thing. I don't know what's wrong with my pen. Essentially the same thing, but I skip, sorry. Okay. I have to add over all these n's, right? I skip the ith guy. In other words, this is simply W minus xi over square root of n. This is just notation for the proof. That's all, nothing fancy. Now, suppose I look at expectation of xi times f of Wi. Anybody know what this is?
Zero.
Why?
Independence.
Yeah, Wi, the whole point of this definition of W is that it does not have xi in it. It has all the other x's except the ith guy. So these are independent. These are not IID, but they're independent. That's what I assumed in the theorem. So they're independent. I can write this as product of expectations, and expectation of x is 0, means 0. Okay, cool. Now let's actually start with the term that I want to bound. I can write this as expectation of the W is simply, I'm just using the definition of W. And then my f of W I write as this. Okay. Then I can write this as expectation of 1 over square root of n summation xi f of W minus f of Wi. What did I do? I introduced the second term, but the term is 0. That's what I just showed you. So I didn't do anything. Okay. Now what I need to bound. Okay, that is only this part, right? The real thing I need to bound is this whole thing. So let me write the whole thing at least once so that we know what we are trying to do. So I'm trying to bound this guy and then absolute value of this. And then I already know that this is sorry. Okay. Okay, so I mean, I just changed the order. Doesn't matter because it's an absolute value. I can change the order. Nothing changes. And then I just substituted this over here. That's all. The summation does not include this. Okay, cool. So we know that W minus Wi is like this xi over square root of n. If I had W minus Wi here, I can happily put xi over square root of n. But I don't have W minus Wi. I have f of W minus f of Wi. So what do you think we should do?
Taylor approximation.
Exactly. Taylor's approximation. So let me write these capital letters in my notation are all random variables. Oh, if that was not clear, so far in everything I wrote, capital letters are random variables, small letters are numbers. So Taylor approximation, let me write it for functions. F of Wi is f of W plus f dash of W, Wi minus W plus f double dash of some guy that is between W and W2 for some Y between W and Wi. Okay, so I want to use Taylor's approximation. So these two terms are kind of like this term. If I send this onto the left-hand side, then I'll have the, then I can replace this by these two things. So let me maybe just directly do it. I'll call this LHS so that I don't have to write it again and again. LHS is equal to expectation of 1 over square root of n 1 over square root of n summation I xi sorry, I'll just follow my notes. I was trying to do it slightly differently and I'm confusing myself. Okay, what I'll do is I'll take this. I want to basically use this Taylor approximation, right? One way of doing it is substitute for this in terms of these two terms. What I'll instead do is I'll add and subtract this term, then I'll substitute Taylor series. So my LHS is going to be 1 over square root of n summation I xi f of W minus f of Wi plus f dash of W times W minus W, whatever, I added some term, okay, plus expectation of f dash of W okay, so I just added and subtracted this term. I mean, there's a plus here because I flipped the order here. Okay, that is the first term. So I just wrote it slightly differently. Here, f dash is inside, this guy's outside. Here, f dash is outside, this guy's inside. That's for this term. Then I have this term. So that I can simply write as a -1 here. Okay. So just add and subtract this term. Now I have two expectations nicely. I can use triangle inequality and split these things as two separate terms. Now I use Taylor approximation to replace this whole thing with this term. So I'll have expectation of 1 over square root of n summation I xi f double dash of y over 2 Wi minus W whole square plus okay. I mean, it's not a big deal. The main thing is to notice you have to use Taylor approximation. After that, it's just plug and play. Okay, very good. Now, what is Wi minus W? By definition, we know that Wi minus W is this xi over square root of n. I don't care about the sign because there are absolute values anyway. So this is going to be 1 over square root of n to, I pulled these two denominators, and then expectation of f double dash of y summation I xi. So this guy is xi over square root of n. This is square. So overall, I'll get cube and I'll get an additional n here. And here, same thing, f dash of w over n summation okay, what did I do here? Remember, this one is outside summation. This one, that where did that one come from? That one came from this guy. This term is outside the summation. So what did I do here? I put this one inside the summation, which means this one becomes n. That's why there is an n in the denominator. This cancels off. I get this. Okay. And for this, what am I doing? This is xi over square root of n. I already have xi over square root of n. So this is xi square over n. Okay. I am pretty much done now. So I just have to dance around a little bit, but I'm almost done with it here. So this expectation, I have absolute value of expectation of something. I can send it inside Jensen's inequality, I guess. Okay. And same thing here. I pulled out the n first, and then I'm sending the absolute value inside. Okay. Then remember the norms that we are using for the functions. At this point, there's only absolute value, but the norms that I talked about earlier are all L infinity norms, which means this guy is upper bounded by its L infinity norm. And this norm is a constant, so I pull it out. So I get this, and then again I use triangle inequality, I guess, and I get this. Okay, same thing here. I bound it by its supremum, that is the L infinity norm. It's a constant. I pull it out, and then I get this. This is slightly weird, so I have to work on this a little bit. By the way, as you can see, I'm actually doing each and every single step. And the reason I'm doing this is because to show how simple this is. The whole point of Stein's method is to make things simpler. And there are, once we came up with all kinds of ideas to develop Stein's method to get this theorem. But once we have the theorem, now I'm not even using my head, just Taylor series, Jensen's inequality, Cauchy-Schwarz. I'm going to use Cauchy-Schwarz in a minute. The usual stuff. These are like just blindly doing the math. So I just promised that I'll use Cauchy-Schwarz. So this is Cauchy-Schwarz, or I think you can also think of it as Jensen, whichever way you like to think of it. Okay, so this is square root of this guy. Expectation of something is less than or equal to square root of expectation of its square, and this is absolute value. I can forget about the absolute value now because there is a square. This is right. That's right. Okay. Sorry, the summation. This one is inside the summation. If you recall from, I should have written it carefully. Sorry, this is misbehaving. Okay, so if you recall, when I went from here to here, this one is inside the summation. I should have put this bracket everywhere. Okay, so now remember that expectation of xi square is equal to 1 because that is my normalization. That is what I assume. Second moment is 1. So which means with summation also by linearity of expectation, this is 1. So what do I have? Think of this guy inside the square as some random variable y. I have expectation of y square here, and I'm telling you expectation of y is 0. This is second moment of some guy whose first moment is 0, which means this is simply the variance of whatever guy is inside. And when you're thinking of variance of something, okay, variance of something, then you can add and subtract a constant, nothing changes. So I can drop this -1. And then this is, and these are independent. So there's sum of variance of sum is same as sum of the variances. And, but this is variance not of x. Remember, this is variance of x square. And variance can always be bounded by second moment. this is second moment of x square, which is x power 4. And that's pretty much it. So this is what this completes the proof. This is what I have in the theorem statement. I have it 3/2. I have the third moments. I have n. I have n, and then I have square root fourth moments. 3/2 here, third moments, n, and then square root, and then the fourth moments. Any questions? So again, the proof, there is nothing. You start with the left-hand side, do Taylor series. And this W, I think, is just like it's notational convenience. It's not really a trick, I guess. All you do is Taylor series and then bunch of triangle inequalities, Jensen inequalities, Cauchy-Schwarz. So in some sense, this was a very simple setup. So we didn't have to do much work. But once people figured out, I mean, the nice thing about a simple proof is that if a proof, suppose you look at Berry-Esseen Theorem and then it is several pages of proof, and then you want to generalize it to something else, that's it. You don't know. I mean, among these 10 pages proof, something could break down somewhere. Here, given that this whole thing is so simple, then maybe you can generalize it to other settings. So this is already general beyond the usual central limit theorem in the sense that I'm not assuming identically distributed. I am only assuming independence. What if I throw independence? Well, you can always come up with a counterexample. Let's say all the x's are identically same. They're almost surely the same guys. Then these things will not be true. But then what if the dependence is somehow very weak? Then can one prove central limit theorems? And the answer is yes. And there are many, many theorems that people have proved for various notions of dependence and things like that. And then as you go through, so as you raise the stakes, as you make the result you want to show more and more stronger, then the proof is obviously going to become more and more complicated. But your baseline is something so simple, so that enables you to do more things. And but then as things become complicated, maybe you have to find new tricks beyond Taylor series Cauchy-Schwarz. And that's indeed the case. And one thing that people have used a lot in the Stein's literature. So basically, if you look up Stein's method, there are almost like many different sub areas, maybe not sub areas, many different problems, issues that people try to address. One is proving a Stein's result for an arbitrary distribution. That is what we discussed in the first part. In the second part, what people's goal is, if you focus on normal. In fact, there is a whole community that does Stein's method for normal approximation. That's it. They don't look at other things. There are books on only normal approximation alone. No other approximation. There are books on Poisson approximation alone. And in the normal approximation, their entire objective in the whole book is to bound these things. But they want to do it in more and more general settings. And for that, they have developed all kinds of fancy tools. Essentially, coupling is going to be an important thing in all of these things. And there are all kinds of keywords. I threw in a few keywords in my notes: exchangeable pairs, size bias coupling, zero bias coupling, equilibrium coupling, and so on. Earlier, I alluded to a beautiful survey paper by Nathan Ross. And in fact, if you look at his survey paper, whatever I did so far is just in the first few pages, 5 pages or something like that. And it's some 60-70 page paper. And most of the remaining paper is spent on explaining all these various techniques. And then he gets like versions of central limit theorem under various notions of correlations. Questions? Okay, so I'm mostly, if I go back to my outline, we did this, maybe I should take this. We did this, that was before the break. We already did this. But before I go to the fourth thing, I want to spend a little time talking about the 3 steps in the Stein's method and where they're coming from, all of that. So remember, 3 steps are, the first one is finding a Stein operator. Second one is solving the Stein equation. So let's talk about Stein operator. Where do the Stein operators come from? I already gave you the punchline that they are generators of Markov processes. Let's actually think more about why they work. So I'll just call this discussion. This is part 4 of my notes, if anybody is following the notes. So I'll answer 2 questions here. question 1 is, where do Stein operators come from? Okay, so Markov process, generators, these are all, I don't know how many of you actually are familiar with these notions, but instead of thinking about it in full generality and worrying about the rigor, the proper formulation, let's restrict ourselves to DTMCs. Special case of Markov process is DTMC, where the state is discrete, time is also discrete. Obviously, I can't, using a DTMC, I can't find a DTMC whose stationary distribution is Gaussian, because Gaussian is continuous, but that's okay. At least I can use this DTMC approach for Poisson distribution or whatever. And then once I figure out the main idea, then of course I can always make it more general using the machinery for Markov process. So what is a DTMC? There is a state space, X, which is countable or finite. And there's a transition probability matrix, which is an X cross X matrix. If X is countable, it's not really a matrix, it's an infinite matrix, but nevertheless, I'll call it a matrix. And then I'll assume this is a nice enough DTMC. What do I mean by that? It is positive recurrence, stationary distribution exists, possibly a irreducible, whatever nice things. I'm not going to get into the technicalities of that. And then let's say the stationary distribution is pi. And then what is the stationary distribution? It simply solves this matrix vector equation. So pi is a row vector. So this is a matrix. X is a set of state space. This denotes the size of the set. This is a matrix of this side. And this is vector. This is a row vector, sorry. So this is a row vector. And then pi p equal to pi, you need to solve this to find the stationary distribution. The same thing can be written as pi times p minus I equal to 0. Now, what is this? This is a matrix. I will left multiply by a row vector. So the whole thing is a column vector. Sorry, is it a column vector or row vector?
It's a row vector.
Row vector, good. That's what I wanted. So it's a row vector. So now I can take my favorite column vector. This is a column vector. Hit it on the right side. I should get 0, obviously. Okay. What is this? This is a X cross 1 column vector, which means it looks like this. If your states are 1, 2, and so on, it looks like this, which means this is actually a function. So functions and vectors are the same thing, right? Only difference is if my state space, if my domain is discrete, functions can always be written as vectors. So essentially, I have a row vector. I'm multiplying with my favorite function. I should get 0. I can think of this as an operator. So I can think of this. So the same equation can be written like this, for example. What am I doing here? Think of this guy as a column vector. F is a column vector. I multiply by matrix, I get a column vector. So column vector can be thought of as a function. So this whole thing is a function. And then I'm just taking expectation of that function with respect to pi. So if X is a random variable with distribution pi, then these equations are basically the same. I'm just going from matrix vector notation to the expectation notation, nothing new. So, okay. When I wrote this, I said that think of this entire thing as a function. What is this function actually? You originally started with a function f, and then I apply an operator to this function. What's an operator? It takes a function, it spits out a function. So this is a column vector. You transformed it in new column vector here, which means this matrix is an operator. Matrices are the simplest kind of operators, linear operators, right? So, okay. So what do we have? Without doing anything, without breaking any sweat, I already showed you that if I have a Markov chain and X is a random variable distributed according to its stationary distribution, then I have something like this, where A is simply an operator. A is P minus I. You know, P of a transition probability matrix, P the transition probability matrix, I just subtract I. Okay, very good. Now the question is the converse true? Does expectation of A f of W equal to 0 for any f. By any, I mean, it has to be nice enough. I think in discrete case, I don't have to worry about niceness, about continuity and so on. This is discrete after all. Maybe I have to worry about existence of expectations and things like that. So for any nice enough. Then the question is, does this imply that W is distributed according to the stationary distribution? And it's not hard to see that the answer is yes, because what I can do is, this is discrete after all, I'll just take indicators. The F's that I take are 1, all zeros, then a single 0, 1, all zeros. I'll take all these F's. And then if I apply that to each of this, then essentially I can characterize each and every component. Then it's not hard to convince yourself that the answer is yes. So essentially, if I have a Markov chain, then I basically prove the Stein's result. I say that think of this P minus I as a Stein's operator. The first thing is that expectation of A f of x is 0 if x is stationary distribution. The second thing is that if the same property, expectation of A f of W is 0 for for all f's for your favorite W, then your W must have the stationary distribution. Okay. Now all that is left to do is generalize this DT from DTMC to a continuous state setting, a Markov process. So firstly, to go from DTMC, the first step is to go to a CTMC. So in a CTMC, you don't have a P matrix, you have a Q matrix. Q matrix, also called the generator matrix. In fact, you can think of Q as the analog of P minus I. P minus I indeed becomes Q. So in CTMC, the A operator is simply the Q matrix. And then from CTMC time is continuous, but state is discrete. So if you go to a general Markov process where both state and time are continuous, then even some of the basic things you do about DTMC and CTMC become non-trivial, and then you have to break your head, all of that. But people have done that. All these theorems exist. And then basically there's a generator of Markov process, which essentially in some sense can be thought of as generalization of the notion of P minus I. And this is the reason why generators of Markov processes are good candidates for Stein operators. So in fact, like I was saying, most popular ones. So during the break, we were chatting about how there could be many Markov chains with the same stationary distribution. There could be many DTMCs with same stationary distribution. Similarly, there could be many Markov processes with the same standard normal as the stationary distribution. Which one do I use? You can actually use any of them. But for example, for Gaussian, the one I showed you is the most popular one because it lets you bound certain quantities easily and so on. And more generally, so for Gaussian, I said that the Stein operator is generator of OU process. For exponential, they use generator of reflected Brownian motion. So you know what a Brownian motion is. You put a barrier at 0 and then make sure it doesn't go to 0, and then it reflects off so that it's always positive. Exponential only have positive support, right? So that's why you have to do this. Then for Poisson, question, can you think of a Markov process? This is discrete space, so Markov chain, continuous or discrete, I don't care. DTMC or a CTMC, whose stationary distribution is a Poisson process.
Infinity.
Sorry?
Infinity.
Yes, infinity Q. In fact, that is the operator that that is standardly used for Poisson approximation. So I said there are books on Poisson approximation, right? The Stein operator they use is basically the generator of infinity Q, which is basically a birth-death process. Good. What else? So if we take a step back, when you do a typical stochastic process course, the whole narrative sounds like this. Oh, okay, here is my Markov chain of interest. It models something, I don't know, it models an epidemic process, it models a queue, or it models some finance process, whatever. Here is a Markov process of interest. This Markov process, if it's nice enough, it has a stationary distribution. Can you find the stationary distribution? If you can't find it, can you find some other quantities like mean under the stationary distribution, things like that. So it's always going from Markov process to the stationary distribution. Stein's method takes this backwards somehow. what it says is, I'm interested in this distribution, this standard normal. I'm not starting with any Markov process. My objective is to bound distances to standard normal. Now I go around hunting, finding a Markov process whose stationary distribution is a standard normal, because there is always like a dichotomy, an equivalence between a Markov process and its stationary distribution. Now, to understand my distribution of interest, if I find a Markov process whose stationary distribution is the guy I'm interested in, then I can exploit the properties of this Markov process somehow to understand my stationary distribution. So in other words, it's taking whatever you learned in a typical stochastic process course and putting it on its head. And turns out Stein's method is not the only one that does this. In high dimensional probability, there is literature on what is called as Poincare inequalities and log Sobolev inequalities, which can be used for high dimensional probabilities. As I understand it, is at least a big chunk of it is basically establishing rates of convergence of probabilistic limit theorems. When you talk about rates of convergence, then one specific example is rates of convergence of a Markov chain to its stationary distribution. In other words, mixing results of Markov chains. And essentially, these inequalities somehow relate to this concentration, the mixing rates. So mixing rates and these Poincare inequalities are equivalent. So if you have a Markov process whose mixing rate you know, immediately you can get a Poincare inequality for the stationary distribution. Now, let's say you have OU process, you know its mixing rate, then you can get a Poincare inequality for Gaussian. Now, suppose you have some other Markov process whose stationary distribution is Gaussian, then you can use this Poincare inequality that you already know for Gaussian and go back and then establish the mixing rate of the new Markov process. So you can basically go back and forth. So this connection between going back and forth, not going just one direction, going both ways, is exploited a lot. One in Stein's method, two in Poincare and log Sobolev inequalities. Okay, very good. Any questions so far? Okay, so this was, so once I proved the Berry-Esseen theorem, the first question I started with is, where do Stein operators come from? If you go back to my 3-step summary of Stein's method, the first thing is to identify Stein's operator. I already explained where they come from and why they are of that form. The second thing is the Stein's equation. If you think about how I introduced Stein's equation, it was wishful thinking, right? I'm like, I really wish this equation is satisfied, my life will be good. And then I go around solving it. But is there something deeper to it? Is this equation, does this equation have a meaning? I'll explain that now. Again, I am copy pasting this guy. Okay, so question 2 is, does the Stein equation that I pulled out of a hat, my wishful thinking that I was dreaming about, have a deeper meaning? The answer is yes. There are at least 2 ways of thinking about it. Both of them are related. I'll only talk about the first way of thinking about it. I don't think I'll have time to talk about the second way. The second method is related to the Lyapunov functions. Lyapunov functions somehow come into picture. I'll talk about Lyapunov functions in the next part of the talk. The first answer that I want to give is, this is actually the Bellman equation. This is Bellman equation. If you have a MDP or a Markov reward process where h is your reward function, then fh, then this equation where you're solving for fh is essentially the average reward Bellman equation, and fh is the value function. Okay. So if you know the words that I talked about, you understand it. Now I'm going to explain what I just said. So again, let's think of a Markov chain. x1, x2, and so on, Markov chain. Same setups, state space, transition probability, ergodic, irreducible, positive recurrent, stationary distribution, pi exists, all the nice stuff. Okay. Now let's say, usually when a Markov chain is doing its thing, you sit and watch, you don't get anything out of it. You're just watching it for fun. Now I put a twist. I say that you get a reward. If I am in state at time k, the reward you get is h of xk. Xk is the state at time k. H is a function that maps the state space to real numbers. And then I give you this many dollars. This can be negative also, which means I take money from you. Okay. Then my question is, what is the expected long run average reward that you get? Let's say this H is nice enough, bounded, whatever. Let's not worry about things blowing up to infinity, stuff like that. Yeah. Bounded, let's say, for the time being. We'll worry about other things later. Yeah. What's the answer? Anybody?
Stationary distribution.
Yes. This converges to a number. What is this number? It's essentially the stationary expectation. This follows from Markov chain ergodic theorem. Markov chain ergodic theorem says that forget about the expectation here, forget about the x. These guys, forget about the expectation. These guys essentially converge to the stationary distribution or the stationary expectation. So even if I drop this expectation, this is true in almost sure sense, but let's not worry about those technicalities. Bottom line is that this converges to the stationary expectation. In other words, if I want to write this in matrix vector notation, it's this. This is a row vector. This is a column vector. Okay, very good. One thing to notice, this is a typical ergodic theorem, which means your initial state doesn't matter. I don't care where you started. The long-term average amount of money you're making is like this, which means your total reward up to time n, let's say, is like n times g. The amount of money you're making is blowing up to infinity with n. That's why the average is a constant, right? Now, so in this viewpoint, I told you that the initial state doesn't matter. If I look at the total reward, the question is, does the initial state matter? Total reward up to time n, let's say. So which means I'm looking at something like this. This is the total reward. Let's say I tell you that I start in the initial state little x. Then turns out this guy is like n times g plus g of x. So let's say Xyway starts in some state 0. I start in state 1. Our long-term average reward is g, but we are greedy people. We after a long time we are both millionaires, billionaires. But then turns out that I started in a better state than Xyway. So my money is $1 billion and $10, $1 billion plus $10. Xyway has only $1 billion. So he's upset, greedy guy. So that is captured by this g of x. In other words, if I divide by n on both sides and take the limit, this guy is irrelevant. But this j of x captures the offset, the extra money I can make by starting in a good state versus money I lose by starting in a bad state. So, I mean, this can be made formal by saying that this converges to this as n goes to infinity. That's a weird thing to say because something is going to infinity. So you can say that this minus this in the limit converges. Let me write it like that. This minus this in the limit converges to this j of x. This j is called the value function. The way I explained it, it looks as totally useless. If you're making $1 billion, why do you care about this $10? If your money is going to infinity, why do you care about this additive constant? In that sense, you don't care about it, but it plays an extremely important role, which I'll talk about in a minute. I was going to say something else. Okay, one thing to notice is that if I take expectation on both sides of this equation with respect to stationary distribution, this is a number, take expectation, it's the same number. This guy, on the other hand, if I take expectation with respect to the stationary distribution, that's like saying I start in the stationary distribution. If I start in the stationary distribution, at every time the reward I get is the stationary expectation, which is g, which means the expectation of g of x, this is true for all, expectation of g of x according to the stationary distribution is 0. Or in other words, if I think of j as a vector, pi j is 0. Okay, and I'm not proving anything here. I'm just stating one has to prove that this limit exists and you're calling it j of x, blah, 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 blah. I'm not proving anything at this point. Okay, good. Now the thing is that one can show that this g and j satisfy the following equation. G plus G of X is H of X plus expectation of J of Xk plus 1 conditioned on Xk equal to X for all X belongs to X. Why is this true? Let's say I want to find my total amount of money after a long time. Let's say n is very long. Then the total amount of money, if I start from state X, is this much. How do I get this much money? First at time 0, I get this much money, right? After this, I go to some other state. Let's say I go to some state Y. Let's say I go to state X, X1. If I'm in state X1, I have to look at the remaining money I'm going to make starting from that state. How much money is it going to be? N minus 1 times G plus J of this. Because I mean, I'm now, my horizon is 1 less, right? This is all very hand-wavy argument. So this N minus 1 cancels and I'll get a G, and I have to take expectation of this over all next states. So I don't know which state I'll go next. So I have to add up over all of them and weigh by appropriate probability. Then essentially I get this equation. Okay, so this is called the Bellman equation for average reward. Markov reward process. Those of you that know Markov decision process can recognize this. This is Markov reward process is simpler than Markov decision process. You don't have a control. Okay, good. Yes.
So just a clarification. So this is what Weizsäcker calls the relative value function, right?
Exactly. Yeah. Actually, you're right. I think I should call this a relative value function. This is not
like students might be familiar with that. Thank you.
Correct. Thanks. Okay. Yeah, if you're familiar with this, then you have seen this. I was just trying to explain the Bellman equation.
No, it's good. Some people might be familiar, many will not be. So it's okay.
Yeah, because at least in my circles, if I write down the discounted reward Bellman equation, everybody recognizes. Average reward people struggle. That's why I wanted to go with the average reward. Okay, so this equation, this Bellman equation, is true for all X, for every state X. If I want to write it in vector notation, it looks like this. J, now I think of it as a vector, is equal to H is anyway a vector, Pj. This expectation can simply be captured. This is one-step transition probability. G is a scalar, remember, but I need a vector, so I put a E. E is all one's vector. So GE is basically a column vector that looks like this. Okay, good. Now, let me write this equation. So what I'm saying is that this expectation is simply P times J of X. Again, how to think about this? J of X, if you ignore P, this J of X is a function. You have to weigh over the next step probabilities, right? If I start in state X, what are the probabilities of my next state? Those are the Xth row of this P matrix. So the whole thing is simply like this. So basically, this is summation Pxy J of Y. That is what this is. Another way of thinking about it is J is a function, P is a matrix, so it's an operator. Pj is what this operator spits out. Look at the Xth component of the Pj thing. So think of P as an operator. Okay. Then what do I have for the Bellman equation? I have H of X. I'll send this G onto the other side. Minus G is equal to, here I have J of X. I said this is Pj. So I'll have P minus I J of X. True for all X. Okay. Do you remember still what G is? G is the steady state expectation. So it is H of Z conditioned on Z being the steady state. Anybody like this equation? Any comments on this equation? This is exactly my Stein equation, if you recall. So this is the Stein equation I saved here. Let me bring it down. I missed some terms, whatever. Okay, so this is exactly my Stein equation. H is your favorite function. So okay, before that, let's take a step back. On the average reward Bellman equation, so I said that G and J satisfy this equation. The converse is also true. So any G and J that satisfy this equation are indeed the relative value function and the average reward. That's actually not quite correct, because if I add a constant on both sides, it's always true, right? Because I can cancel this, which means the G is unique. The solution of this equation is not unique. G is a unique solution, but J is not unique up to an additive constant. So to find the right J, you have to use the fact that pi j equal to 0. But let's not worry about that. That's irrelevant for the purpose of our discussion. What we care about is that the solution of this is unique up to an additive constant. So now what I'm saying is the Stein equation is essentially this, which means what Stein equation is trying to find is, given a h, it wants to find this fh. What is this fh? It is simply the relative value function of the Markov reward process, where in state x you get reward h of x. So Stein equation is, in other words, just the Bellman equation. By the way, the Stein equation, I should have told earlier, is also sometimes called the Poisson equation. And then we now showed that it is the Bellman equation. Except that everything I explained so far, I explained in the discrete time, discrete state setting, but then I sneakily changed this to A. And then the idea is that everything should go through. I don't know if this is done in great generality for Markov processes. For CTMs, for continuous time, discrete state, it's done. But essentially, the idea is that it's the same Bellman equation one would expect in more general settings. And why is a Bellman equation showing up here? Why should I find this FHs? So for H, I have to find FH in Stein's method, right? Why are these FHs the Bellman equations, the relative value functions? Turns out the relative value functions are the best Lyapunov functions in some sense. And that's the reason we are trying to solve the Bellman equation to find the right Lyapunov functions. So if you understand what that means, that's good. If not, I'll try. I don't know if I'll try to explain this in detail later, but at least I'll show you how Lyapunov functions can be useful in the next part. Let's take another 10-minute break, and let's convene again at 11:25, let's say, 8-minute break. So we'll start at 11:25. I'm happy to answer questions in the meantime.
Yeah, this stuff is awesome. You guys can take the break if you want. This was a really helpful explanation.
Cool.
Yeah, thank you. So one thing I'm thinking is that you want the relative value function to be well behaved. And so, for instance, you would want, just qualitatively, you would want your Markov chain to mix well, because otherwise it will not be well behaved. So fast mixing is one sort of qualitative thing that you would want.
I see. I think that thing that you talked about, the mixing behavior of Markov process and its connection to the stationary behavior, that is what is explored in this log Sobolev Poincare inequalities in some sense. That's one way of thinking about it. Second way of thinking about it is that usually these mixing arguments are studied using Lyapunov drift, right? So suppose I have some dynamical system, and then I have like v dot less than or equal to minus v. I know that v is decaying like e power minus t, and the dynamical system is going very fast to its stationary distribution. So Lyapunov arguments capture the mixing behavior. So if you go from here to the stochastic setting, whenever you get a generalization of this, like a one-step drift, and then possibly some other terms, then you can convert those into rates of convergence. That's what I'm doing in my stochastic approximation work. So what they are saying is that the one-step drift, of course, depends on the one-step transition probability matrix. But if you're able to find a right Lyapunov function, then that will imply good things about the rates of convergence. And that is essentially what you said. But the only difference is normally in Lyapunov approach, I try to find some Lyapunov function. I try to make guesses so that the equations I want are satisfied. But turns out the correct Lyapunov function. What do I mean by the correct Lyapunov function? The guy that gives the exact equality in some sense.
Yeah,
that is actually
the relative value function. Yeah.
We are trying to find the value functions here.
Yeah, after contemplating on this for a couple years with Fang Yu's work, like I reached the same conclusion, like maybe earlier this year, I think.
Oh, I see. So this actually Shrikant told me. The Bellman connection Stein equation being Bellman equation, that was Shrikant's observation actually. Then the Lyapunov thing, I can't remember. Maybe Shrikant told me, or maybe I came up with it. I can't remember.
Yeah. I mean, these things keep coming up. Recently, I think they have this paper, Itai, Gurvich, and Banerjee. So they call this Bellman inequalities.
Correct.
So if you want to make it tight, then basically you should align the Lyapunov function with the relative value function.
Correct. I mean, we did one of their papers in our group meetings. I think you were also there. You logged in remotely again.
Yeah.
Yeah.
We also covered that in class.
Oh, I see. Okay. In fact, actually, this whole connection can very nicely be exploited. So Shrikant, in his latest version of MDP course that he taught, he wanted to do the average reward Bellman equation. And then instead of doing it the usual way in a typical book, he first said that suppose I have a Lyapunov function that satisfies some condition. Then that gives me the following steady state bounds. Now, if I have equality in the Lyapunov function, I should have the following equality. And that essentially gives him the Bellman equation. So
Right.
he proves the Bellman equation from a Lyapunov argument.
Right. Yeah, that's a little bit backwards in my mind, but okay, got it.
Yeah, I had a question.
Yeah.
So is there any Berry-Esseen which is for not normal?
What do you mean not normal? Where the answer is not normal?
Where Z is not normal.
What do you mean by Berry-Esseen? Are you saying that you want to look at these guys and you want them to converge to something not normal?
Yeah, is it possible? You can
That
show
I don't
that
know. But instead of these guys, I can come up with something else here. I can come up with some other sequence of distributions that can converge to not normal.
but then do you know this finite bounds?
Yeah. That is, for example, you probably remember from undergrad math probability course. Binomial converges to Poisson under appropriate scaling, not scaling, appropriate limit. This is binomial n comma p. Sum of n Bernoullis whose probability of winning is p. I'm letting n go to infinity, p go to 0, and np converges to lambda.
No, but you need a Berry-Esseen formula for it, right?
Right. So rate of convergence of this is done. So what I'm saying is the distance, I forget what distance, is less than this. This is done.
You know the function of n, basically.
I don't remember, but
you will get some function of 1 over n, n square.
I don't know if it is n or square root of n or what it is. I have it in my other notes. So this is done using, this is Poisson, right? So you have to use Stein's method for Poisson approximation to do this. In Stein Gaussian, the simplest result is the Berry-Esseen. For Stein Poisson, this is the simplest result. And people have generalized this in in many other things. What if these Bernoullis are not independent?
But then in the Berry-Esseen, you don't need to assume anything about the distribution of the exercise. But this is looking very special if you assume they are binomial.
You can generalize that also, I believe. Yes, you can generalize.
But the cool thing about Berry-Esseen is it doesn't need an assumption of the distribution of the exercise. You just
no. What I'm saying is, so this is a summation exercise, right? I'm saying this exercise is Bernoulli in this result. But there's a general version where these exercises are not Bernoulli. It's an exercise IID with mean that is going to 0 and n going to infinity.
Okay.
That also is IID. If they're not IID, if they are independent but not identical, that is also done. If they have some weak amount of dependence, not independent also, that is also done. All this goes under, I said there are entire books on Poisson approximation, right? These are the kind of results they prove there.
I'm also wondering about this thing, Stein equation that you're talking about. In some of the simplest SDs that you can write down with diffusion term and I think you just take a minus lambda fx is the drift term. Your generator of the Markov process is going to be what? It's going to be the heat equation. You're going to get the heat equation back. So I'm just wondering what you're looking at what you're calling the Stein equation. Is it then just equivalent to heat forced TA? Is a forced heat equation?
I think so. I mean, there are deep connections to the whole PD literature. That's correct. I don't know enough about those connections, but But people who
what-
work in the space do exploit those connections.
Your script A is then the Laplacian.
Possibly.
So your generator of the basic ADs is a Laplacian differential operator. So what you're looking at is basically forced Laplacians.
Again, 4, 5 hours.
I see. Okay. Possibly. Yes.
I've already read parts of it before.
You think your memory is so
That's why they call this Poisson equation. Actually, not just Laplacian, Poisson equation. The reason it's called Poisson equation is because of the connection that you just mentioned.
Yeah. Right. But then the point is this. When the Stein's equation is the Poisson equation, that has to come from the very specific kind of SDs.
Correct.
many open problems. It's cool.
But then you don't know how to solve the SD. You don't know how to
That's the
find-
problem. Yeah.
You're saying you want to discuss. Yeah.
So in some sense, all these are connected. So if there is a known answer in one thing, if the solution of the heat equation is known, then you can basically use that here and then nail this down. If something on this end is known, you can use that for heat equation. So this is building bridges across all these areas.
Yeah, the question really is like, when you have a forced Laplacian equation, exact solutions are very hard to find. What are examples of forced Laplacian equation with sources for you to know of exact solution? That's very tricky business.
I don't know. That's why I said solving Stein equation more generally is hard. It's hard exactly for the reason.
And I'm just wondering, what I'm trying to connect in my head is this. There are SDs known where you can write the solution of the SD exactly.
Correct. Like OU process.
So when you can write the solution exactly, does that somehow lead you to have a better control on what the system distribution is?
Exactly. That's why for OU process, life is good because you know the station distribution, you know the transient, you know everything.
But if I know the solution of the SD, does that lead me to a control on station distribution?
Yeah, you does, right? You do, right? Like for OU process, you solve the Fokker-Planck equation, and that gives you a lot of control. That actually tells you that the station distribution is exponential. It gives you rate of convergence. Okay, I think maybe we can take this offline because I should restart the third part. I have. So yes, should we restart?
Yeah. Between 1 and 2, it will be a problem. Okay, folks, is anybody outside? Can you just call them?
Okay, I'm still going strong after 2 lectures, third lecture.
Yeah, you are the most energetic. So good.
Okay. I don't know how you guys do it, like 3 lectures in one shot.
Yeah, it's one of those rare occasions. I feel like there are almost no questions, and still it's because it's so clear that we all follow it.
Oh, okay.
I mean, I hope. I was looking around. I think people are like, they're keeping up with you.
Okay. That's nice.
Is that right? Yeah, I think so. That's pretty awesome. Okay.
Thanks.
Yeah, we can start, but there's 1 or 2 people who are gonna just walk in at some point.
Sure.
Yeah.
Okay, so Anirudh was asking me about, so I said that Stein's method can be, you can develop a new Stein's method for any distribution of interest, and then you can use that to prove rates of convergence to that distribution. You can develop Stein's method for Poisson, show rates of convergence to Poisson. Develop Stein's method for exponential, show rates of convergence to exponential. So Anirudh was curious about other distributions. So in the last part of this talk, I'm now going to show you an example where the limiting distribution is exponential, and then we'll establish rates of convergence. And this example that we are going to talk about comes from queuing theory. I'm not sure how much queuing you saw in this course, but I think at least you saw max weight and stuff like that. So you must know basics of queues.
Yeah, we did. We covered this max weight as a Blackwell policy, and then we covered mirror back pressure.
Oh, okay, cool. Yeah, you have already seen a lot more than what I need anyway. So what I'm going to do is a very simple single server queue. There's arrivals, and then there is servers. There's infinite waiting space. Okay, I mean, I have some notes on why queuing theory is important, all of that. I think I'm going to skip. We are now in math mode. If I was just starting the lecture, I would have spent 5 minutes talking about data centers and all those things now, I think. I'm not in a mood for it. Okay, so the point of, so the simplest queue one can think of in continuous time is an MM1 queue, where the interarrival time is Poisson. It's a continuous time system, firstly, continuous time stochastic process, birth-death chain more specifically. Interarrival times are Poisson, service times are Poisson, and then a customer comes. If the queue is empty, they start service. If the queue is non-empty, if there are other people waiting, then the customer will wait in the queue. And whenever they start service, they need an exponential amount of time. After that, they depart. If the queue is empty, the server is idling, otherwise no. And it's known that the stationary distribution of MM1Q is geometric with whatever parameters. Then one can talk about GG1Q. GG1Q is a continuous time queue where the interarrivals are IID from an arbitrary distribution. Service times are also IID from an arbitrary distribution. In general, the stationary distribution is unknown. Unknown not because people couldn't find it, it's not an open problem. It's not possible to find an exact expression for this because the way the stationary distribution depends on the interarrival and service distributions is very, very complicated. People have found some transform connections between these, the connections between the MGFs of these guys and so on. And one can use these connections to come up with, to numerically compute the distribution whenever you need it. And there are efficient numerical methods and so on. But this is not satisfactory, especially for a theoretician. You tell me that you have some system, the fundamental question I can ask about it is stationary distribution, and you tell me you don't know how to compute it. Then I can ask you, can you at least tell me the expected queue length, expected number of jobs, or expected waiting time? And then the answer is, again, you cannot find exact answer. Then I'm like, fine, I'll lower my bar. Can you at least give me some bounds on the expectation? That we're able to do. And this was done by Kingman in 60s. This is typically taught as Kingman's bound in an undergrad class. Maybe they don't do the proof, but I will do the proof now. But what I'll do is, instead of looking at a GG1Q, I will think of a discrete time system. It turns out that this is actually equivalent to GG1Q. Q length in my discrete time system I'm going to present in a minute is same as the waiting time in GG1Q, because both of them satisfy the Lindley's equation I'm going to present. So whatever I do, this is also applied for GG1Q, but I like to think of everything in discrete time because that's what I'm used to thinking about crossbar switch and so on that Yash mentioned. So now time is discrete, and in each time slot, arrivals happen at the beginning of time slot, and then at the end of the time slot, services happen. The number of arrivals in each time slot, A of k, is number of arrivals in each time slot. Now I'm not talking about inter-arrival time. I'm talking about number of arrivals. That's why it's different from GG1Q. Number of arrivals in each time slot is IID, and then mean is lambda, variance is sigma A square, A for arrival. And then for simplicity, I'll assume that this is bounded support. The bounded support Amax assumption can be relaxed in some settings. In some settings, we still don't know how to relax it, but I'll not get into those details. And the number of services in each time slot is also IID. So this is IID, and then this also has mean. I'm calling it mu, variance sigma S square, and this is bounded by S max. Okay, and then I can ask, what is the queue length at time k plus 1? How does it depend on the queue length at time k? So if there are queue number of customers waiting right now, so many new customers come, and then among them you serve so many. This should be the new queue length, as simple as that, right? Not quite. Suppose I have 0 customers. Suppose I have 0 arrivals. Then how many customers can I serve? So I have to clarify that this S I'm talking about here is called potential service. What this says is that the number of people I serve in each time slot is random because of various reasons. And if I had enough customers waiting, in this time slot, I could have served 5 customers. But if I don't have any customers because there are no arrivals and queue length is empty, then I'm not going to serve anybody. My queue length cannot go to -5. I can't say that now I'll serve 5 imaginary customers that will compensate later. I can't borrow service for future. So what I should do is I should do this bracket plus. What is bracket plus? If the thing inside is positive, this bracket plus doesn't do anything. If x is greater than or equal to 0, it is 0 otherwise. It basically doesn't let you go negative. And pretty much all of queuing theory is this bracket plus. Because if the bracket plus was not there, this is just a linear equation. And then I can do whatever I want with a linear equation. This bracket plus introduces non-linearity. And this also is related to the reflection I was talking about. This Q is like a random walk. It goes up, goes down and all that. But then it can't go beyond 0 with the bracket plus. That's a reflection at origin. And if you look at GG1Q and look at its waiting time, it satisfies an equation that looks like this. This is called the Lindley's equation. And the whole thing is a Markovian system. Okay. So in particular, let's think of an example. Suppose A and S are Bernoulli. So suppose lambda and mu are less than 1, and then A and S are IID Bernoullis. So in each time slot, you have an arrival with probability lambda, no arrival with probability 1 minus lambda. Any customer that is in the system, if there are customers in the system, one of them will depart with probability mu, will not depart with probability 1 minus mu. Now, if I look at the inter-arrival time, then that is geometric. So I can think of this as a GO1Q, geometric inter-arrival times, geometric service times. This is the discrete analog of MM1Q. This is one particular special case, and its stationary distribution is again geometric. This will be a discrete birthday chain. So again, I can answer anything you want to know about it. Life is good, but I'm not interested in this special case. This is not what I'm interested in. I'm interested in this more general case. Okay, so okay, I said that all of queuing theory is about this bracket plus, but then since it is not linear, I actually don't like this bracket plus. I like linear equations. So what I'll do is I'll make it look linear. Notice that this A and S don't depend on what is happening inside. The number of customers that are coming in the current time slot don't care how many people are already waiting. A is independent of Q. S also is independent of Q. The real service depends on number of people in the system. If there's no customers, I can't serve anybody, obviously. That's what, but S is not the real service. S is the potential service. So S is independent. The number of customers I could have served now does not depend on anything. It's independent of everything else. But I may not serve so many customers. The number of customers I actually serve is S minus U. This is real service. This, of course, depends on the current queue length. So U depends on Q, A, S, all these things. So what I did is I wrote an equation that kind of looks like linear. But of course, I mean, I can't, by introducing notation, I can't make the difficulty vanish, right? So this U is a very complicated object. It depends on everybody else in this equation. But, and I have to deal with it. So let's actually write down what this U is. So, so I said, if the thing inside is positive, then bracket plus does not do anything, which means in this case, U should be 0. If the thing inside is negative, if this guy happens to be negative, what will you be? You will be some value, so that the whole thing will be 0, which means you should just be the negative of this. You should be the negative of this. I'll just put absolute value when this guy is negative. Okay. So one thing to notice, so somehow I have to deal with this complicated U, and the way I'm going to deal with it is using this elegant relation. What is this saying? So why is this true? Firstly, very simple. I'm multiplying these two terms. Suppose U is 0. Oh, by the way, all these guys are non-negative quantities. Q is non-negative, A is non-negative, S is non-negative, unused service is also non-negative. Okay. Suppose U is 0, multiply by anything, it is 0. This is obvious. Suppose U is not 0. Why is U not 0? Because this Q plus A minus S would have gone negative. So U came to rescue you to make sure this doesn't go negative. So the amount of value it will take will be just enough so that this whole thing is 0. So whenever U is non-negative, whenever U kicks in, whenever the reflection kicks in, then Q length at the next time slot should be 0. So if U is 0, the product is 0. If U is non-zero, This guy is 0. So this whole thing is 0. In other words, whenever the server can idle only if there are no customers in the system. So if there is idling, U is unused service. U is unused service. If there is unused service, that's because the queue length at the next time slot is going to be 0. Okay. So this is the central equation that is going to help us do many things. Okay, very good. Now, in these systems, the first question that I care about is this thing even stable? Will Q blow up to infinity or not? Is the Markov, this is a discrete time Markov chain, does the stationary distribution exist? I have to worry about irreducible aperiodicity, those issues. I assume it's irreducible. I can make some assumptions, some very, very mild assumptions on the arrival process to ensure that it is irreducible. But I'm worried about stability. So it is proved that by stability, I mean positive recurrence. So those of you that have done Markov chains, you know what positive recurrence means. If you haven't seen it, think of it as existence of stationary distribution. This happens if the arrival rate is less than the service rate. If arrival rate is greater than the service rate, then the queue will blow up to infinity. So that is unstable. If they're equal, it turns out it is null recurrent. So we'll only care about lambda equal to actually, let me write the other thing also. It is null recurrent if lambda equal to mu. It is transient if lambda is greater than mu. So this is unstable. This is like critically stable, but we don't want to be here. This is where we want to operate. Okay, so how is this shown? This is usually shown using something called the Foster-Lyapunov theorem. One way of showing something is positive recurrent, a Markov chain is positive recurrent, is to find the stationary distribution. But here that is hard. And Foster-Lyapunov theorem gives you a prescription. It doesn't tell you what the stationary distribution is, but it actually tells you that the Markov chain is positive recurrent if you can verify some conditions. We'll not get into all of those. Let's say that we believe this. I use Foster-Lyapunov theorem. I know it is positive recurrent. Now I want to find the stationary distribution. I can't find it. So now the first question I'm going to ask is, can I find the expectation of the queue length? Okay, I told you already that I can't find this. Then can I at least find lower and upper bounds? Okay. Any questions so far? Is the setup clear?
So are you going to prove something about the GG1Q?
I'm not going to explicitly state about GG1Q, but everything I'm talking about is applicable for GG1Q. Because you have limitless recursion in GG1Q, except that this arrival you should interpret this as inter-arrival time, this is the service time, something like that.
Oh, SK is the inter-arrival time.
I think so. When you go from here, it is the number of services in the discrete model. But look at the limitless recursion for waiting time of GG1Q. It looks exactly like this. You'll get WK plus 1 equal to WK plus UK minus VK. One of U's and V's is inter-arrival time, another one is service time. Oh, and then you assume, yeah, that's what I was trying to say. Yeah. So it's the same equation. So all the results are applicable. You should just reinterpret them.
Got it.
Okay, cool. So the approach we are taking to adopt to answer this question is a Lyapunov approach. I start with a Lyapunov function. In this case, quadratic Lyapunov function works. Where did I get this Lyapunov function? Actually, to show stability, you need a Lyapunov function, and it's the same Lyapunov function in some sense. But whatever, think of it as I pulled it out of a hat. Based on experience, if you want a Lyapunov function, the first thing you should try is quadratic. If that doesn't work, then you can think about other things. Okay, what I'm going to do, the key step in this approach, the key conceptual step, sorry, I will abuse notation and I'll use V of Q to denote V of QK. Okay, yeah, V of QK. And V is a function of Q actually, but I'll make it function of time. So in steady state, let's say at time K, you are in steady state. This is important. In steady state, the expectation at any time is same as the expectation at the next time. This is definition of steady state in some sense. So this equation, I call this setting drift equal to 0. Setting drift equal to 0 just means saying that the expectation doesn't change in steady state. Because you can think of this minus this as the drift, as the one-step change in the Lyapunov function in some sense. And I'm saying in steady state, the change should be 0. Okay. This is always true, but I'm going to start with this and I'm going to do some manipulations. So if I start with an equation 3 equal to 3, and then I add some things on both sides, subtract some things, life will be good. If I start with an equation infinity equal to infinity, and then I send them onto the other side, and then says, what, I add 1, and then cancel the infinities, I get 1 equal to 0. So in order to do anything with this, I need to first check that this one is finite. If it is infinity, I can prove nonsense using this. This will be wrong. Okay, so I need to check this. I'm going to skip that step 2. I'll get that for free when I use Foster-Lyapunov theorem. So I'm going to check skip that. So the main message I want you to take from the third part of the talk is setting drift equal to 0, finding the right Lyapunov functions. And of course, Stein's method will show up eventually. And whenever you can always set drift equal to 0, but you should, before that, check that the expectation is finite. If not, you can, what you get is nonsense. Okay, good. So let's do this now. Expectation of this function at time k is equal to expectation of this function at time k plus 1. And what is qk plus 1? I know qk plus 1 in terms of qk. It is just this equation. This is the definition of a q. I'll substitute that. Actually, before substituting that, you can substitute that right here. But to make the calculation slightly easy, I found that it's convenient to first do this. I add and subtract the UK. So the thing is, why do I have this K? This K is actually steady state. This is steady state. But at steady state, I want to compare 2 consecutive times. So I'm introducing K and K plus 1 to, like in my head, to keep track of that. But their expectation should be the same. But if you have them together, then you have to worry. The correlations, I don't know what the correlations are, but the expectations are the same. Okay, very good. So I'll use a plus b whole square formula. Okay, so when I write this, I have to use k's all over the place. And then I'm too lazy to write k's. So I'll drop k's. So instead of a of k, I'll just write a. U of k, I'll just write u. Q of k, I'll write q. But then how do I write qk plus 1? This I'll write as q plus. Okay. This is just shorthand. Actually, in the papers, I put all the k's properly. Okay. I used a plus b whole square formula. Now let's look at this term. What is this term? It is qk plus 1 times uk. What do we know about it? 0, exactly. So I killed this term. That is the key step in some sense. U terms alone I can deal with. A and S terms I can deal with no problem. Q and U terms are somehow hard. In single server queue, that becomes 0 very easily. And other systems that one can study, like load balancing or crossbar switch that Yesh mentioned, the main difficulty, the heart of the matter is to figure out how to kill this term. We'll not get there today. Okay, very good. Now, I'll substitute for qk plus 1. Qk plus 1 is qk plus arrival minus departure plus unused service. So q plus minus u is going to be q plus a minus s. So I'll substitute that here. I'll get q plus a minus s whole square plus, I have u square here. I have minus 2u square. So I'll get a minus u square. Again, I use a plus b whole square formula. Somehow one of the most advanced tools I use in all my research is this a plus b whole square formula. When it doesn't work, then I have to make an equivalent of it. Okay, then I get expectation of q square here. Left hand side, by the way, what is left hand side? It is expectation of qk square. So this nicely cancels off. That's good. And then I'll have expectation of a minus s whole square plus 2 expectation of q. Why can I write it as product of expectations? Because the arrivals and potential service, S is not service, it's potential service, they're independent of the queue length. So I don't care what the queue length is. The number of customers coming in, don't care how many people are there, they just show up. Service, potential service is also the same. Q, I cannot do that. Q and U are not independent. That is the problem. That's why the cross term was so difficult to deal with. If I had QU term, I wouldn't know what to do with it. But if it is Q plus times U, then because of our definition of U, that goes. That's the reason I danced around a little bit so that I get this Q plus U. I got rid of it. Now I don't have a QU term. That is the hard part. As long as that's not there, I'm happy. Okay. Then this is just lambda minus mu. Remember, lambda should be smaller than mu. Arrival rate should be smaller than the service rate. I will call that epsilon. Epsilon is defined as mu minus lambda. You'll see why. So now I can bring that term onto the left-hand side. Then I'll get the epsilon expectation of Q is equal to, so this term I sent to the left-hand side. This is 2, I guess. And then now let's focus on this term. It's somebody square, second moment. Second moment can always be written as variance plus mean square. Mean, of course, is epsilon or minus epsilon, whatever. And the variance, because they're independent, is sum of the variances. And then I have this expectation of U square. I have to deal with this expectation of U square. Clearly, expectation of U square is greater than 0, obviously. Less than or equal to, what is U? U is unused service. I could have served 10 customers because my S happened to be 10, but I don't have 10 customers. I only have 8. Then there is unused service of 2, which means U is upper bounded by S. And S, on the other hand, we assumed is upper bounded by S max. Okay. So now what is this expectation of U? I want to find expectation of U. I need to do some work to do this, but not too much work. I again find yet another Lyapunov function. Let's say we had, earlier I used quadratic Lyapunov function. Now I just use regular linear function. And then for any function, I can set this. I already showed you that claim that expectation of Q square is finite. Then expectation of Q is clearly finite. So I can set drift equal to 0. Then what I get is I can again write this QK plus 1 as Q plus A minus U S plus U. This cancels with this. Then I'll get expectation of U is equal to expectation of S minus A, which is epsilon. This kind of makes sense. On average, forget about the actual queuing process. On average, in long term, I'm getting 10 customers every time slot. On average, I can serve 10.5 customers every time slot. Then the amount of wasted service is 0.5. That is exactly what this is saying. Okay, so this is a digression. Now I go and put it here. Then I have that this is less than or equal to S max. Now I can go back to this equation right here. Then I'll have 2 times expectation of Q less than or equal to sigma S square plus sigma S square plus epsilon square minus epsilon S no. Yeah, this is true. On the other side is, okay, I should have written it. Okay, I just take this equation. This guy, I have lower and upper bounds. I just put those. I have to change the order because it's a minus, that's all. Okay, okay, good. So now I can send the epsilon onto the other side. What will I get? Plus okay, good. So as I told you, I don't know the exact answer for this. I don't have a formula for that, but I gave you upper and lower bounds, and the bounds, whatever this thing is, that part is same. They differ by this S max. Oops. They differ by this S max. Okay, fine. Then let's understand this bound. Sorry, I forgot to put the epsilon here. Okay, so what is this saying? Remember, what is epsilon? It is the slack, lambda, mu minus lambda, the difference between the service capacity and arrival rate. And we know that lambda must be less than mu for stability. If lambda is equal to mu, I don't have stationary distribution. It's not positive recurrent. It's not stable. So epsilon must be positive. And what this is saying is, as epsilon goes to 0, this Q length is blowing up to infinity. How is it blowing up to infinity? It's blowing up to infinity at rate epsilon. sorry, at rate 1 over epsilon. And then since it is blowing up to infinity, I can ask what is the behavior of epsilon times q as epsilon goes to 0. So firstly, I can ask what happens to this. This is the steady state q length that depends on epsilon. So now the way you should think about is I have a sequence of systems. In the first system, I have some epsilon may be equal to 1, and I have steady state distribution. Second system, epsilon 0.5. Third system, epsilon 1 over 3, 1 over 4, and so on. I look at this sequence of systems. I look at their stationary Q length, expected Q length, and then I ask what happens to this expected Q length in the limit. Why am I doing this? Actually, I'm interested in the expected Q length of one of them. You couldn't give me an exact answer. I mean, you gave me upper and lower bounds. That is something, but I'm not completely happy. Okay, so at least I want an equality, at least for something. So now I'm asking, if I look at the sequence, will something happen in the limit? And unfortunately, the Q lengths are going to infinity. But you know that the Q lengths are going to infinity at rate 1 over epsilon. So then I can ask, since Q is like 1 over epsilon, I'll multiply it by Q, by epsilon. And then I ask, what is the limit? Then I can take limit on both sides here, multiply by epsilon. This goes to 0, this goes to 0. If I multiply by epsilon, this also goes to 0. This epsilon will cancel off. And then upper and lower limits are the same. So I get an exact formula for this. So essentially, I'm saying that the expectation of Q length for small enough epsilon is sigma square over 2 epsilon. I'll use sigma square to denote this as a shorthand instead of having to write two things. They always appear together. Okay, so what this is saying is that the Q length can be approximated by the variance over 2 epsilon. That's essentially said in this inequality anyway, but this is a limit theorem now. It says that Q length multiplied by epsilon in the limit is exactly equal to the sigma square root. Any questions so far? So this is very similar to, so if you have never heard of central limit theorem, the first thing you would do is you would look at empirical averages of IID random variables, and you'll ask, will it converge somewhere? And then someone tells you that, yeah, it converges. Maybe you don't know law of large numbers also. Then what you can do is you can ask, what is the variance of this? And then you can calculate the variance, and the variance is like 1 over n, which means the variance of this is going to 0 at rate 1 over n. Then if you're interested in what happens in the limit, then you can ask, okay, fine. Actually here, this is equality, so there is nothing else to ask, but you can multiply this n onto the other side. If you send inside the variance, you'll get a square root of n. And then you can ask, what is the limiting variance of this? It is 1. And then you can ask, so this is simply this guy. Then you can ask, now I don't care about variance. Does this converge in distribution to something? And central limit theorem comes and tells you this guy. So far, so think of this as step 1. This is step 2. And step 3 would be, what is the rate of convergence to the standard normal? We actually did step 3 today. What was that? Square root of n, I think. Yeah. So the first step is, even before thinking of central limit theorem, why should you do this scaling? The reason you should do the scaling is because look at the empirical average. Its variance is converging as 1 over n, which means the standard deviation is 1 over square root of n. It's going to 0. If I multiply it by square root of n, I'll get a non-trivial answer. Once I multiply by that, then I can ask, the beyond this mean square thing is the in distribution is something nice happening. And by the way, remember, this is usually shown with characteristic function method. Here I just calculate the variance. There is nothing much there. That's one line proof. And here I'm using Stein's method. In my queuing system case, this itself is non-trivial. What I did so far is explain to you this step. And then what this is saying is that the Q length is actually like 1 over epsilon. That is what I got here. Then if I multiply by epsilon, I'll get a non-trivial limit. That is what this is. So this and this are called Kingman's bound. I mean, the first one is bound. The second one is a heavy traffic limit. This limit as epsilon goes to 0 is called heavy traffic limit, because lambda is approaching mu, arrival rate is approaching service capacity. And so the traffic is heavy. That's why it's called heavy traffic limit. So then I can ask, now that I know that this sequence of processes, this sequence of random variables, sorry, for every epsilon, I have a q epsilon. Epsilon multiplied by q epsilon is a sequence of random variables. Now the question is, this epsilon times q of epsilon in distribution, does it converge to something? That will be the step 2 or the question 2. the next question I can ask. Is this clear? Any questions so far?
Just a simple question, sorry.
Yeah.
So this restriction that you need to S to be bounded with some constant.
Yeah.
It means that you cannot assume the exponential distribution here, right?
This is discrete anyway, so you can't have exponential. You can think of some other unbounded discrete, like, I don't know, geometric, Poisson, and so on. Those are not allowed. You're right. But everything I state so far, this result, okay, if S max is, if there is no bound, you cannot get this result, but you can get this result. This is true even without S max. And this result is true without S max. We can prove that. The lower bound becomes more complicated. That's all.
Okay.
Okay. The only thing I can't prove without S max at this point is the Stein's method part. Maybe that is also true. It's just that we haven't thought about it yet.
Awesome.
Okay, good. So to answer the second question, I actually can show you the proof. The answer is yes. The answer is that this converges to an exponential distribution with mean sigma square over 2. This is the mean. One way of thinking about it is as follows. So you all know that for MM1Q, or for the Bernoulli 1Q, the discrete analog, the stationary distribution is geometric distribution. And if I look at the mean of this geometric, that also will go to infinity as epsilon goes to 0. Then after I multiply by this epsilon, I can actually do it by hand and then see that it converges to exponential. But here, I don't know the stationary distribution of GG1, so I can't do it by hand, but I can show that this epsilon q converges in limit to exponential. This is like saying, if you're thinking of central limit theorem, if your X's, IID guys are Bernoullis, then you can find the distribution for any empirical sum by hand using binomial thing. And then you can by hand show that it converges to Gaussian. I think that was the very first central limit theorem that was proved some 200 years ago or whatever. But then the point of central limit theorem is that it's true even if you can't find the distribution of this guy explicitly. Same story here. Okay, now how do we prove this actually? So this result, so let's call this theorem 2. Maybe I'll call this theorem 1. Theorem 1, I proved it to you. Kingman did this in 60s. Theorem 2 also Kingman did in 60s, actually same year. And the way he proved it is a complicated approach, at least complicated for me, complicated in the sense that it involves heavyweight mathematical machinery, using diffusion limits and so on, functional central limit theorem and so on. Essentially, he shows that the queuing process can be approximated by a reflected Brownian motion in the limit, and then the stationary distribution of reflected Brownian motion is exponential, and then one has to show a limit interchange argument, which is not hard in this case, but becomes extremely hard in other queuing systems, and after that you get this. In other words, if an incoming grad student wants to understand this result, they have to go and do possibly 2 or 3 semesters worth of courses. Then they can read Kingman's paper, then they'll understand this. But few years ago, with my student, I don't know which year, maybe 16, we proved this. We came up with an alternate proof using characteristic functions or moment generating functions for that matter, which you can use any of them. We call this the transform method for heavy traffic analysis. So you can think of this as in the same spirit as CLT. The CLT is usually proved using characteristic functions. Why not use the same thing here? Okay, that's not how we thought about it. That's how I'm explaining it now. But this actually gives a 3-line proof. I should confess that the lines should be long lines. So if it's a real whiteboard, I can go from left all the way to the right, then I can write it in 3 lines. And the main idea is setting drift of a Lyapunov function to 0. And the Lyapunov function we use is the exponential Lyapunov function. And since I'm interested in showing behavior of this guy, I actually put epsilon also here. So using this as the Lyapunov function, setting drift equal to 0, and you have to do some manipulations, especially taking limits, Taylor series, and so on. That's not hard. There is one hard part. The hard part is dealing with U. And we know that U satisfies what? U satisfies this equation. But in the exponential Lyapunov function, it's not clear how to use this equation. You have to use a modified form of it. And the modified form, basically, once you know that equation, proving it is like just not even one line. But coming up with that modified form was hard. So my student Daniela did like reams of pages of calculation to show that this, when she came up with this equation, I said, this is obvious, because if u equal to 0, this is obvious. This guy is 0, so the product is 0. If u is not 0, qk plus 1 is 0, so this thing is 0. So once you transform this into this relation, then the proof is just 3 lines. Okay, that's the part I'm going to skip so that I can talk about Stein's method. Okay, so to do Stein's method here, now I know that the limiting object I'm looking for is exponential. So I'll write this theorem slightly differently. I can write this theorem as epsilon q. I'm putting this epsilon, I'm not using consistent notation. This is just to denote that I have a sequence of stationary distribution for each system. For epsilonth system, this is the stationary distribution. Okay, I divide by this. This should converge to exponential. Exponential has this nice property. You multiply by it, then you still get an exponential, right? So why? Because Stein's method, the way we did it for normal was for standard normal, right? Now I'm going to state Stein's method for standard exponential, the exponential one. So that's why I'm doing this. Okay, so the theorem, if you follow the 3-step procedure that I described in the first part of the talk, and then try to do it for exponential instead of Gaussian, and then use the generator of RBM, reflected Brownian motion, and then solve the Stein equation, all of that. At the end of it, you will get the following result. This W stands for Wasserstein distance. This W is the thing that I want to bound. This Z now is exponential 1. Earlier, I used Z to denote standard normal. Now it is exponential 1. Then this is sup F belongs to FW. Expectation of A F of Z. Okay, I should tell you what A is, what FW is. A is, you give me a function, I apply my operator, what I spit out is this thing. Derivative minus the original function plus f of 0. Okay, and so which means this theorem is essentially saying expectation of f dash of W minus f of W. I have f of 0, right? I have to worry about that. I didn't write it. I didn't write it because the functions I'll be looking at, the function class I'll be looking at are functions such that f of 0 equal to 0, f dash bounded, f double dash is this. Okay. So since I assumed f of 0 is 0, then I can drop this. That's it. So after going through the 3-step procedure, this is what you get. I already gave you what the operator is. The only thing you need to do to prove this theorem is solve the Stein equation. I'm not going to do it. You can find the proof in Nathan Ross's paper. I'm going to use this, but I'll use this slightly differently. So what I'll do is, left-hand side, same thing. Right-hand side, I'll use G instead of F. And then all I'm doing is think of F as G dash. Wherever you have F, you put G dash. This is almost like a change of variable in some sense. There was a question about the operator. In fact, in reality, the operator looks like this. For some reason, they change it, like Ross changed it when he stated this theorem. But the generator of the RBM actually looks like this instead of second derivative and stuff like this. And when this was stated, Ross basically changed the notation. And then now we are changing it back again because this is what turns out to be useful for us. Okay, and then what am I interested in? The W I'm interested in is now think of it as so in the previous theorem, epsilon was going to 0 and it is this limit, right? Now I want to bound distance of my epsilon q epsilon divided by sigma square over 2 and then the standard normal. This is what I want to bound. And then so I think of epsilon as fixed for the time being. Okay, and then if I bound this guy, I'm done. I'll get the rate of convergence here. And the rate of convergence is actually going to be order epsilon. We'll see that. How am I doing with time? Have 10, 15 minutes?
We usually end around 12:15 or 12:20 maybe.
12:20, okay.
So meaning 10 minutes.
10 minutes. I think I can do it in 10 minutes. If I skip some calculations. I want to state the main thing. So if you recall, the way we applied Stein's method for central limit theorem, we basically used Taylor series, and that's pretty much it. And then the fact that the W was sum of IID random variables. Here, I can't, this Q, I don't even know what this Q is, right? It's not sum of anything. It's a stationary distribution. So I have to somehow get the stationary distribution into picture. And the way I'm going to do it is using by setting drift equal to 0. So I will use W to denote this as a shorthand. And what I'll do is expectation of f of q plus, think of q plus as qk plus 1, that's our shorthand, is equal to the same thing as. So pretty much this is the only new idea in this proof. Everything else is Taylor series and somehow dealing with that u terms, generalizing that qu equal to 0. Generalizing u equal to 0 and then setting drift equal to 0, setting drift of a function equal to 0. These are the only two new ideas. Taylor series, Cauchy-Schwarz, that is standard. So relative to the CLT proof, Berry-Esseen proof, this is the new stuff. And again, why? Because earlier you had summation xi divided by square root of n here, and you can add and subtract, you know their ID, you can exploit all those things. Here I have a quantity, I don't know what it is, and then I have to prove these bounds on this guy. So to get this bounds on this q infinity guy, earlier when you asked me to find expectation of q length, I had to, all I did was I found a Lyapunov function, set its drift equal to 0, got bounds on q length. Now you're asking me to find expectation of some weird function of q length. So again, I'll do the same thing. I'll pick yet another weird function, set its drift to 0. And then if I pick these functions carefully, so I should hopefully get this kind of bound. That's the intuition. Okay, good. Now, I know q plus minus q. Qk plus 1 minus qk, I know what it is from the q evolution equation. I don't know f of q plus minus f of q. These are just constants. Don't worry about these things. They're just sitting there. So again, I should use Taylor series. So except that now I'll go to one extra order. That is the only new thing here. Earlier, I think I truncated at the second order. Now I will truncate at third order. And then z is between y and x. Okay, so then instead of y, I put this q plus thing. Instead of s, I put q thing. And then f dash of x, which is the q thing. And then this is y minus x. What is y minus x? It is going to be 2 epsilon over sigma square times q plus minus q, qk plus 1 minus qk, which is a minus s plus u. And same thing for the second order term. Now this guy becomes square, a minus s plus u whole square. And then there is a third order term also. And then instead of y or x, you should have a z here. I'm calling that as q tilde. So q tilde is between q and q plus, let's say. Okay, now I will apply expectation on both sides. Okay, cancel this. This is basically setting drift equal to 0. Maybe I'll focus on, since I'm running out of time, maybe I'll focus on just one or two of these terms. I'll focus on this term maybe. I'll call this term 1. Then term 1 is what? So let's split this separately. This u part and the remaining part, I can split it. If I look at the first part, I'll get, actually, this 2 epsilon over q can be cancelled everywhere. It appears everywhere. It appears here, it appears here, it appears here. Okay, so that guy is gone. Now I have f dash of whatever this is, a minus s plus expectation of f dash of. Okay, so here, same trick as before, q is independent of a minus s. So I can write this as product of expectations. And this guy is minus epsilon. That is good. This part, this is the cross term between q and u. This is the hardest term to bound in some sense. Everything else is easy. So if this f dash guy was not there, then I would just get q times u, and I can probably invoke the qu equal to 0 somehow. But this f dash is problematic. So this is where I can exploit the properties of my function. So unfortunately, this notation is slightly messed up. I'm using this theorem, but then instead of g, I'm using f. I should have used g all over here. So which means my f dash of 0 is 0. So let's think of f dash of x. F dash of x is f dash of 0 plus f double dash of y times x, y between 0 and x. This is again Taylor series for f dash, not f. And then f dash of 0 is 0 because of the function class I'm dealing with. And this f double dash, its norm is less than or equal to 1. Therefore, I have f dash of x is less than or equal to x, which means this term right here can be bounded by expectation of my 2 epsilon over sigma squared times qu. Okay. This qu unfortunately is not 0. Remember, qk plus 1 times uk is 0. Qk times uk need not be 0. Currently, if I have 2 customers, my potential service is 10. There is unused service. There are 8 unused service, but qk is not 0. Qk plus 1 will be 0. So then what I do is I write this qk in terms of qk plus 1 minus qk plus 1. Okay. This whole thing times u. Now qk plus 1 times u is 0. Then I'll have this remaining terms, and that those can be bounded by, I know that each of these is bounded by a max, s max, and so on. And the expectation of this I know is epsilon. So at the end of this, I get from this term. So let's go back to what we had before. I'm almost wrapping up. Okay, good. So here I had 0. Here I had 0. I had a minus s term that gave me a negative term here, right? So I will have epsilon expectation of f dash of the guy that we are interested in. And on the right hand side, I'll get some epsilon term corresponding to the u term that we just dealt with. And then among all these terms, so again, here I can use a plus b whole square formula. I'll get u squared terms, which I can handle because u is like epsilon. This a minus s will give me something non-trivial. So at the end of the day, what I would get is expectation of f dash of this guy minus expectation of f double dash of the same guy. To do this, to get the second term, this is the f double dash. This a minus s whole square, I'm going to use sigma square. I'll cancel some sigma square and so on. After doing some manipulation, I get this term. I'll get this is less than or equal to something order epsilon. Now, if we go back to our theorem, this is essentially what the theorem is saying. I should bound this term. And this I'm going to bound by order epsilon. So what I have is this is the final theorem. Okay, so I mean, to bound all these terms, you had to do some work using Cauchy-Schwarz, a bunch of other things. But the most important thing is to deal with this Q. There, we use the properties of our function class. Remember, the function class, it starts at 0, it is 0, and then its derivatives are bounded. So I think I will stop there. Any questions?
Let's give Siddharth.
Thank you.
So at a high level, you used Stein's method, and then you used the Lyapunov drift argument as well.
Exactly, correct. I used both. The question is, what is the Lyapunov function that I should use? And the Lyapunov function I'm using is this. So that's a very good comment, because in Lyapunov method, if I want to bound some quantity, I have to construct a Lyapunov function. I have to pull it out of a hat. I have to invent or dream up or whatever. What Stein's method is saying is that if you want to bound some distance, let's use Lyapunov method, but then you don't have to invent the Lyapunov function. I'll give you a class. Think of all of these as Lyapunov functions. Use each and every one of them. You'll get a bound. Look at the worst case bound. That will give you the distance bound. That is what Stein's method is saying. And then based on our discussion in the last break, I said that the correct Lyapunov function is the value function. That's the reason these are coming by solving the Bellman equation, the Stein equation.
What is the discrepancy function class here? Sorry, what?
Stein distance. Oh, distance is Wasserstein distance, but the function class looks like this. F of 0 is 0, first derivative and second derivative is bounded.
Right. Very cool.
Cool. It's you can think of it as actually Q square is a good example of this guy. At 0, it is 0. It's a derivative. Sorry, no. Q square is an example of this guy. So derivative of Q square. So Q is an example of this, I guess.
You mentioned that something goes wrong, like you can't use this for a switchback because it's like there's some state space collapse. Can you maybe explain why like that poses an issue for this kind of?
Okay, so the issue is that everything I talked today is about a distribution like Poisson, normal, exponential, which are univariate distributions, single random variable. Now, if you have complicated, and that's why I looked at a single server queue. There's a single queue. If you have more than one queues, if you have two queues and they're interacting in some manner, then the stationary distribution I expect will be a bivariate guy. Now, developing Stein's method in general for these bivariate distributions is hard because solving the Stein's equations there is hard. Does that answer your question? So we extended this result for a load balancing system. There are n queues, but the thing is in heavy traffic, they all behave like a single queue. So the object is still going to be a univariate exponential. That's why we were able to extend it to load balancing. So whenever there is a queuing system which behaves like a single queue in heavy traffic, everything, you can make it work. If it behaves like more than one queue in heavy traffic, it's not clear how to make this work. And the classic example of a system that does not behave like a single queue in heavy traffic is the switch.
So this was the problem which you were trying to work on during Informs, and now you solved it?
No. Actually, we didn't even do any of this. So there, what we were trying to do is step 2. So for switch, so think of the 3 steps. This is the first step, right? For switch, even the first step was not known. This is what I solved a few years ago, my paper with Srikanth. Now we're trying to do step 2 for switch. What is the limiting joint distribution? And that has been an open problem. This is what I've been thinking about for 5 years. And this is where we have like some breakthrough. There are still like one part of the proof technical part that we are still struggling, but everything else is in place. In particular, so far, nobody even guessed what the answer is for the switch. Now we know the answer, even though one part of the proof is has a hole in it.
So is there some connection with entropy between Stein's method and entropy?
Yeah, I was like vaguely thinking about it yesterday while I was preparing. I think one way of thinking about it is that entropy, I don't know, is this some notion of entropy in some sense?
So this might be like how much you're away from the exponential, which is the maximum entropy distribution.
Correct. But I can define Stein's method for any distribution. Your favorite distribution, I find a Markov process and I can do Stein's method.
Yeah, no, so okay, my question is more limited. It's like when you're trying to show convergence to a maximum entropy distribution, does the corresponding Stein's method have an entropic interpretation?
Oh, I see. Maybe there is something, it should somehow be related to this, but I don't know what it is. Gaussian, you can ask the same question for Gaussian, right? Gaussian also is maximum entropy in continuous whatever, right? So yeah, maybe there is, but I don't know what it is. I haven't come across anything like that in my limited, the limited set of papers I looked at.
Okay, that was fantastic. A lot of food for thought. Thank you so much, Sivateja.
Thanks a lot. Thanks for inviting. Thanks for the great questions. So have a good break.
You as well. Okay, folks, thank you for your patience. So we will have a session next time where each of you will present. I mean, each group will present. Stop the recording.